To continue with the Tech Talk presentations, we have 15 finalists in the 3 different categories. So please take your seats and enjoy the show. Thank you very much.
Good afternoon, everyone, and welcome to this edition of the Tech Talks of the Monaco Energy Boat Challenge. This is a place where teams will share cutting-edge technologies, learn, inspire, and compete for awards in innovation, design, and eco-conception. The Innovation Prize recognizes and honors teams that innovate on their boats. It's also a way to push the boundaries of what's possible. I would now like to invite Jérémy Lagarrigue, the head of the Innovation Prize, to the stage.
Thank you, Lilou. Hello, everyone. Welcome to all the students. Welcome to all the professionals after the good conference we had this morning. Welcome the jury member. Another time, very glad to be with you. We will start with the Innovation Prize. Innovation Prize, we have 5 different categories. The first one is we need to see a real innovation. The second one is we need to prove that you already developed a proof of concept. And the third one is really to see that we have an impact and a need in the industry. Please consider that that's one of the 3 main points we need to see and to feel when you do the presentation. And after that, if you have an idea about how you want to develop this technology, how you want to address the need of the marine industry, that will be also another hard point for you in this presentation. We wish you all the best. Looking forward to see you. Congratulations to be part of the 5 finalists. And let's take the floor to the best Tech Talks. Thank you.
So for the Design Prize, this award focuses on not only the technological innovations of the boats, but also on the aesthetics. I would now like to invite Gilles Vernet to the stage.
Thank you all, and thank you for the Monaco Energy Boat Challenge to have this design prize for now 2 years. Now I would like to emphasize the purpose of these design awards. So it recognizes the creativity, the functional innovation, and also the emotions which are generated by the aesthetic of your project. The goal is to highlight the combination of form, function, and meaning, while addressing the specific requirements of the Monaco Energy Boat Challenge, which are environment and technology. This award, as just said, is not just about the beauty or the aesthetic of your concept, but it celebrates your ability to transform, improve, and inspire through your design. Thank you.
And lastly, the eco-conception design, which focuses also on the sustainability aspects and the technologies of the boats. I would now like to invite Lizzie Howard to the stage.
Hi everyone. So firstly, congratulations to those of you that have made it this far. We read some really amazing reports in the lead up to this. And it was really great to see some of the steps that different projects are taking to really show how they are iterating and developing their designs by using life cycle assessment. So from the Eco-Conception Prize, what we're looking for really is for projects that show a holistic approach to sustainability. So looking at all of the varieties of ways that our projects can have an impact on the environment around us, and what steps we've taken as a team to mitigate those, and what we foresee our steps being in the future as well. So we're looking for those projects that have considered their impact at every stage of the life cycle, from the materials they've chosen, the design processes they've gone through, all the way through to the transportation, and then at the end of life of their boats as well. We want to see where the impact hotspots were in your designs and the decisions that you've made along the way. They should be not just about how your boat is now or how it was at the beginning, but also identifying the areas where there is room for improvement and what we see the future in sustainability in this area as well. But yeah, well done again. It was some great reports, and we're really looking forward to seeing you guys bring them to life in your presentations.
So to start off this edition of the Tech Talks, I would now like to invite TU Delft to the stage to present the project. Oui. The teams will have 10 minutes to present their projects with an extra 5 minutes of questions. And once you stop those times, if you go over those times, I will have to ring the bell to let you know that your presentation is over.
Hello everyone, my name is Oliver. I'm the team manager of the TU Delft Hydromotion team. And we're a team that consists of 25 students from the Netherlands, and each year our team completely renews. Now this is quite unique. A lot of teams here have people that have been in the team for a few years, but ours refreshes every year. And this means that we get fresh insights and new perspectives. Of course, everyone here knows about the maritime pollution to the world. We're here to see what kind of innovative solutions can solve this or help address this problem. Because in the end, we would like to go to a world where not only the maritime industry is powered by clean energy, but all the industries are powered by clean energy. The maritime industry contributes about 3% of world CO2 emissions. Heavy fuels and diesel are the most prevalent fuels. But we can change this. Now, this is a very simplified graph. And here you can see the differences of alternative fuels. Left on the bottom, you have batteries. It's gravimetric energy density on the vertical axis and volumetric energy density on the x-axis. And here there are some options. We have hydrogen at 350 bar, 700 bar, or liquid hydrogen. And then there's also some promising fuels in ammonia and methanol. Now we did some research and we wanted to go further into liquid hydrogen. And now we are not saying that liquid hydrogen is the only fuel that will fuel the maritime industry in the future. We're saying that it can be part of the solution for specific ships, not every ship, because there will not be a fuel that's the best for every ship out there. So here's the design of our boat. This is a render, but the tank is actually in it now as well. So if you would like to see, you can come check it out in real life. But as you can see, we started designing the boat when we did not know what our constraints were in terms of size of the tank. So to have some wiggle room, we made the space of the tank on the port side, on starboard side, equally big as the part where our compressed hydrogen tank is, as you see on the bottom. Now, when we decided to go for liquid hydrogen, we hoped that there will be some space free, because that's what we want to show, that there's also alternatives to a compressed hydrogen that have used less space, like liquid hydrogen. And as you can see, almost half of our compartment is completely empty. Now, had we known this from the start of the year, we probably would have redesigned this, made the compartment a bit smaller. But the fact is, we only have 1 year to design, build, test, and race our boat. Because each year we make a completely new design, a new challenge, and something to race with. Now, as you can see, our liquid hydrogen tank contains about 7.8 kilos of hydrogen, and our compressed tank has approximately 8.4 kilos of hydrogen. But it uses 3 times as much space. Now, as you can see, it's not really 3 times, because the liquid hydrogen tank also has some systems in place to eventually use it in a fuel cell. But still, it's almost the compressed hydrogen tank is twice as large as the liquid tank. Unfortunately, this one is very unclear. So that's a bit of a shame. I will just put it here and I will explain what I wanted to say on the previous slide. So one of the challenges with liquid hydrogen is that it's incredibly cold. It's at minus 253 degrees Celsius, or 20 Kelvin. At these temperatures, oxygen liquefies, air liquefies. This is something you want to prevent. That's why we have a vacuum-walled double tank, which means that we have an inner tank with a vacuum layer around it, and then the outer tank. This ensures that there's not as much heat ingress, that there's a minimum amount of heat ingress. This is due to a phenomenon called, which we want to prevent, is boil-off. As hydrogen is so cold when it's liquid, it starts to naturally evaporate. When hydrogen evaporates, the pressure will increase in the tank. And at some point, your tank will not be able to keep all this hydrogen inside. That's why you want to minimize your heat ingress. But what if the pressure does rise? Well, you could use it, of course. That's what you were building it for. Should this, however, not be the case, the tank is in storage for some time, then you could also vent this boil-off, which is a safety precaution. This is not something you would like to do, but it's something there as a safety. Furthermore, we cannot use liquid hydrogen in its liquid form. Before it passes through our fuel cell, which is how we generate electricity and actually power the boat, we need to warm up the liquid hydrogen to ambient temperatures. Because if you put liquid hydrogen to our fuel cell, you will break everything. And that's not something we would like to do. So we use the waste heat of our fuel cell to actually warm up our liquid hydrogen. And once the liquid hydrogen is warm enough, due to our pressure buildup unit, it will go through the piping and pass itself through the fuel cell, which is how we can propel our boat and use every system on our boat. Now, we've also like to talk about maybe the examples that are already out there. Here on the left, you have the MF Hydra. This is a Norwegian ferry, and it is the only ferry in the world that's powered by liquid hydrogen. It's because there's quite some logistical challenges. You need to be able to bunker the liquid hydrogen somewhere, which is definitely a challenge, as it needs to be kept on those immense cold temperatures. But they've done this. It was a technological challenge, but they've made this a reality. A boat completely powered by liquid hydrogen. And now we're lucky to be in Monaco, because this ship here on the right, actually, it was laying in the bay here some days ago. And this is also a boat that is not completely powered by liquid hydrogen, but this is a yacht made by Fedship, and they also use liquid hydrogen as a range extender. Also something to showcase that the technology and know-how is already there. Now, we've also, at the conference this morning, had someone talk about the energy observer. Here you can see a concept of a cargo ship powered by liquid hydrogen. Now, this is also not completely powered by liquid hydrogen, but it is one of the main energy providers on the boat. So we see that there is some demand for liquid hydrogen. Factories and producers are able to produce this, but still, demand and supply are not matched. There's a bit of a chicken and egg problem, as has been stated a few times this morning. People, or like us or other companies, might want to introduce liquid hydrogen, but because there's so little infrastructure yet, no one really can start. But the producers are waiting for people to demand the hydrogen. So something needs to be done about this, like subsidies or just very bold action by companies. Now, obviously, this is very risky, and this is why it's probably not really happened before. But for us, it's a bit different. We're students, we can dream, and in just 1 year, we've made it a reality. We work together with the people who've done the teams before us, who know systems of the boat, and we work together with more than 100 companies to be able to make our boat a reality. I see our team as a team that just combines the knowledge that's already in the field and just shows that it's possible if you really want to. Now, obviously, we are a student team. We do not need to make a profit. That's true, and I can sense maybe some cynicism in that. But it's just, if we can show that it's already possible in 1 year and done by students, that we think that if companies take the next step, that it is possible. I would like to thank you for your attention. Our boat is right now currently out on the water, sailing on compressed hydrogen. So thank you for your attention, and if you have any questions, I look forward to hearing them.
Thank you and congratulations. Do we have some questions on the stage from the jury? Look, everyone is ready to build a hydrogen liquid vessel. Okay, I do have one. As we have some students in the team and also some industrials, could you please share the hardest point by using liquid hydrogen this year? If you have to share this experience with them in order to avoid the mistake, avoid some bad decision, in order to give the floor some idea about the mistake you have done in order to help them to be better than you.
Yeah, for sure. So for us, it's been mostly logistical problems. It's, well, it might be a very stupid answer, but one of the most difficult things about making a liquid hydrogen-powered boat is actually acquiring the liquid hydrogen itself. Yeah, it might be a very tedious thing, but if you want to acquire liquid hydrogen, it's usually either nothing or you get a truck of 10 tons. And on our small boat, that's not something we can really use, of course. So for us, it was a really big hassle, and we had to work with research institutions that then get it from the factory themselves. But if you make a deal with a supplier somewhere, then it's probably a lot easier. And we have also had some time delays with our tank itself. But all in all, I think that we were able to do a very much in just 1 year.
And another question concerning the liquid hydrogen is the boil-off. Everyone is scared about the boil-off on hydrogen. So could you give us an idea about the different timing of boil-off depending on the size of the tank, and how do you decide to use this size of container?
Yeah, of course. So basically, for our tank, we have a boil-off rate of about 5%, which is quite a lot. I can imagine you think, well, 5%, if you lose that in 1 day, that can't be a sustainable option. Well, that might be true, but once you scale up a liquid hydrogen tank, this actually becomes less, and you're not talking about 5%, but you're more going to 1 or 2%. And if you have a big enough headspace, then you can actually keep the boil-off gas in your tank. And once you can use the hydrogen, you can pass it either through a fuel cell or, so you can use the energy as well. So it depends on how you use the boat, but if you're able to also passively use the hydrogen that boils off in maybe a smaller fuel cell for your support systems and the batteries, then you don't lose a lot of energy at all, actually.
And then last question, but also very important, because most of the people are scared about hydrogen, most of the time because it's high pressure. By using liquid hydrogen, you decrease a lot the pressure, So in a way, you reduce the risk. So could you share a bit the risk analysis, the risk that you felt by having a liquid hydrogen? Was it in a way as easy as using a gas? There was some point a bit harder. What was the experience in between the complexity of using liquid hydrogen compared to compressed hydrogen, or was it a sort of easier way that you anticipated? Because I saw that was something you were sharing a bit before in the presentation that was very nice to hear.
Yeah, so that's a very good question, actually. Basically, hydrogen and liquid hydrogen are very different things, and you walk against very different problems. Now, I think that because liquid hydrogen has not been used a lot in small quantities, that for us it was a bit harder to do proper research into what happens if you only have little amounts. A lot of studies have been done exploring things for maybe container ships and tanks that are bigger than our boat. So that was one of the harder things to do, actually. But what makes it easier is that you're not working at immense pressures, because for our hydrogen system, we need to pressure test everything multiple times with nitrogen first, and then make it be able to withstand pressures a lot higher than we are using anyway. But it's different, I would say. But I think that if you have the proper tools and enough research, that liquid hydrogen is easier to handle. And it's also definitely for bulk transport, liquid hydrogen is easier.
So now for the design award, I would like to welcome Team Sea Sakthi to the stage, please.
Vanakkam, good evening, and bonjour. It gives me immense pleasure to stand in front of this esteemed gathering, esteemed dignitaries, and the audience. A warm evening. To introduce myself, I'm Nityashri, and this is my colleague Kamalika, and we'll be the presenters for the day. Before presentation. And we are from Kumalgur institutions with a 4-decade legacy. And it is situated in Coimbatore, Tamil Nadu, India. India, when we talk about the place which we come from, it is holding rich regional, cultural, traditional heritage and architecture and whatnot. Marine technology is something commendable. From then, we wanted to take inspiration from our very own country. So when we started searching for that, we had something called the Chola dynasty, which is remarkable and still echoing in every corner of the world. The Chola dynasty excelled in everything. Their architecture soared the skies, and their marine technology conquered the waves, and their bridge between the ocean and the land was commendable. And that is what Team Sea Sakthi really needed, the perfect blend. And with that, there's something in the architecture which is called a the trunk of an elephant, the face of a lion, the body of a horse, and the tail of a serpent. And these together make it the best. And that powerful guardian, which was long slept in the pillars of the temples, is now rising in the waters of Monaco, presenting Liali 4.2 to you, ladies and gentlemen. Now, we have inspired these Yali's curves into our cockpit. And these curves not only make it aesthetically beautiful, but there is also something more technologically significant. What made us fascinate was that these curves reduce the air drag very significantly. Also, this unidirectional nature makes it more stronger and sleeker. This is not just theoretical calculation, but practical reality. Because last year, we had a speed of about 14 knots, but this time, after these curves, which made it faster, made it to 20.3 knots, making Yali sharper, sleeker, and faster. And we have to give it life. That's where the material science comes to play. And we always evolved in our material science since the first year. And last year was a major breakthrough where we used eco-friendly material like pineapple fiber in sandwich with carbon. But this time, there's no place for carbon, because complete sustainability means only eco-friendly materials. So balsa and flags in the sandwich method with different waving patterns has given us the best structure. Talking about the weaving patterns, this balsa is considered the lightest wood, and the 2x twill gives us the maximum strength to weight ratio, thus making it lighter but more stronger. And the flag's unidirectional nature gives us the best structural rigidity. Also, I would like to quote something from last year. We used reinforcement ribs for the structural rigidity of the cockpit. But these Yali's curves and the weaving patterns of the materials we used completely eliminated the need for the structural ribs and making Yali more stronger. And thus, this is the essence of the cockpit of Yali 4.0, drawing design from ancient wisdom, reflecting our sustainable values. Yali is sailing towards the era of excellence. But do you think Team Sea Sakthi stops there? There's more. Over to Kamalika.
So yes, Team Sea Sakthi does not stop there. We have the ergonomics. Every design that we made this time is human-centric. Every path we chose is human-based. And this ergonomic analysis where we made is based on the human height being 183 centimeters. And we also evaluated the cockpit with our pilot's own rapid upper limb analysis. This actually gave the cockpit not just the aesthetics, it gave the cockpit and the pilot the comfort to drive, the position to sit, and the proper posture while racing. And then we have the cockpit with a streamlined structure. Not just being a normal cockpit, we have a cockpit with sleek structure. But this does not stop there, right? This cockpit is evaluated for its streamlined structure, and that's how we were able to reduce the air drag for the cockpit. And we were able to increase the speed, as she said, up to 20.3 knots this year. So that is the streamlined analysis of the cockpit. And being a progressive team for 4 years, we just do not stop there. We reuse and repurpose wherever possible. And in that way, the year's upcycled plastic seats and the aluminum bars of last year has found new life in Yali 4.0. And being a team of progressing for 4 years, Yali 4.0 has been the past and been in the present as well. Now let's talk about the power. This whole powertrain system is designed by Yali 4.0 by ourselves. This powertrain is fully propelled by an axial flux motor. This axial flux motor is very unique as it gives us a 94% efficiency, but just 11 kgs of weight. And interestingly, there is no cogging or jerky effects during the low speeds. And to support this system, charge for the racing, as well as we are able to have a higher temperature withstanding capacity during the endurance race or any long race that happens during the course. And the powertrain. The propulsion system was indigenously made completely by the team itself. Something innovative and efficient about this propulsion system is that this lower unit is inspired from the torpedo itself, the missile itself. That's how we were able to get a hydrodynamical and an efficient lower unit, and this lower unit is supported by spiral bevel gears. Not only stopping there, we have custom-made 3D printed propellers, which are adaptable for different race conditions and different courses of the race as well. And when we talk about lightweight and lightweight materials, the clamps that we created for this cockpit is made out of aluminum and has the lightest weight ever. This is precisionally engineered to have proper trim control for the propulsion system as well. So these are some of the few design integrations that I would like to introduce you Yali Edge, our newest data acquisition system. This data acquisition system has 3 main important categories, starting with predictive maintenance, active analysis, and real-time telematics. This predictive maintenance is something which will tell us that there might occur a problem or an error in the system so that we can rectify it beforehand. Active analysis is an AI-assisted system which will help us to know that the course is happening this time. We don't need a man to help and to analyze the data personally. And the real-time telematics is where we can know how is the state of the battery and the motor as well. And moving forward with that, Yali has been a progressive team, and introducing you all YachtOS 2.2. Last year, we had YachtOS 1.2, but we just don't want to stop there. This YachtOS is being integrated into augmented reality as well. And I just don't want to explain YachtOS for you guys. I want you guys to experience it. So let's all dive into YachtOS. This is the augmented reality class that we have for YachtOS. For example, let's just wear this glass and see how it looks. We'll move forward. Now, for example, our AI is listening to what is happening there. Now, let me ask the AI to give me the course for the slalom. And see, the AI reads my voice and gets me the course for the slalom that I need as perfectly as it can. And there's no need for any other manual help for the pilot to know about the course of the slalom. Just the AI assistance is enough. And not only there, this YachtOS 2.2 provides the augmented vision, where this will provide us the podium stand we are in, the SOC of the battery, the performance of the boat, and everything just in these glasses and nowhere else. It is very efficient for the pilot to just drive around with those glasses. So that is Yali's innovations and design implementations of this year. And being a constructive team, we have a constructor cost coming around 19.597, as well as our whole boat all the way from India to Monaco. We have it all around 60. So Team Sea Sakthi does not stop there. We don't stop as a racing team. We are a team towards sustainable motives. And we are here to preserve maritime heritage through education and innovation. And we have taken a huge step towards all that all through years. So that is Team Sea Sakthi's design presentation. Nandri, thank you, and merci.
And we are delighted to ask any questions. The floor is now open.
Any question in the audience? So thank you very much for your very enthusiastic and global presentation on the project. One small question. You've spent a lot of time explaining the relation between the original ID and the cockpit design. And you talked about airflow and reduction in the airstream of the cockpit. Why did you left the gap in between the cockpit and the engine box or the battery pack, and not connected the two to get just like one long cockpit?
So, thank you for the question. So to answer that, so our previous in our previous boat, we have implemented a sleeker, continuous cockpit all the way from the pilot to the energy system. So what we analyzed was that the weight where we can reduce, we were searching for where to reduce the weight because we had weight constraint last year. So that helped us to eliminate a significant amount of weight. So we went for this kind of design aspect. Yes.
Thank you.
If there is no question, I have plenty of questions. Can I? Not only on the design. Huh? If you go back on your sunglasses with IA, I think that's something all the students are looking for because, and also in the industry, that's really something that we'll need. Are you really using it, or can you give it to another team so they can test it or not?
Yes, so we do have this as a prototype. We can give it to the other teams. So what we thought was we last year made sure that we gave all our resources in open source, and we'll make sure to do that this year as well. And yeah, we'll be very glad to share it with other teams.
Congratulations for that. Do we have other question? In fact, I have maybe another last question. I have to say, as a part of the jury, you amaze me every time you made the speech.
Thank you.
Sometimes a bit too much, you know. But at the end of the day, we have to say that you deliver, so that's quite amazing. It's a pity we just have one team from India, so could you please help another team, another Indian team to come and join the event?
Yeah, sure, sir. We do have our president here of our institution, so with the help of him, yeah, we can connect other universities as well. Yes, thank you.
And next time, maybe you'll see a lot of Indian teams. And maybe we'll promise that.
Looking forward for that. Thank you so much and congratulations.
Thank you.
Thank you, Team Sea Sakthi, for this amazing presentation. I would now like to move on to the eco-conception finalists, Uniboat.
Good morning, everybody. We are Chiara and Lorenzo. We are two members of the Uniboat team from University of Bologna. We are here today with you to talk about the Eco Prize. As you all know, the health of our planet is a very important issue that concerns us all right now. And so we should move all together to find sustainable and alternative solutions to those that we already have. So, as a team, we invested our time and our money to find this type of solutions. So, our key points were recyclability, sustainability, and waste reduction. About the recyclability, many of our components are recyclable, but we moved farther. We're trying to find sustainable solutions even for those materials that are not recyclable at all. For example, the carbon fiber. About the sustainability instead, many of our components are made of natural fibers, such as the flex fiber and leather made from orange skin and cactus. And about the waste reduction, instead, our components that we manufacture by ourselves this year in carbon fiber are not made in virgin carbon fiber, they are made in expired carbon fiber. This way, we can get the same performance, but we manage to reduce the waste. So let's take a look. We have natural fibers, expired carbon fiber, and recycling carbon fiber. This year, we decided to fully renew our boat. And so we redesigned it. And we were provided by Northern Light Composites with a brand new cockpit. This is made in a composite material made of flex fiber and thermoplastic resin. Now, which are the advantages of using these materials? Flex fiber is not really much used in the marine sector. But we decided to use it because it's natural first, very low impactant on the environment. It's lightweight, but still quite resistant. About the thermoplastic resin, this is a very valid solution because instead of using thermosetting resin, this is recyclable. Now, let's take a look all together about some numbers. We have some data about the carbon footprint of several natural fibers, of several types of fibers. First, on the top, you will find the virgin carbon fiber, which is the most impactant at all. Following, you will find the recycled carbon fiber. And you may notice, you should notice, how the impact is drastically reduced just by recycling the carbon fiber. Following, you will find the glass fiber. And last, which is the less impactant, you will find the natural fibers. About the natural fibers, if we consider both mass and economical allocation and either the CO2 uptake, you will notice that we may consider it not only carbon neutral, but its impact might even be considered to be negative. And this is why, for this reason. It's because when the plant grows, it sequesters CO2 from the atmosphere. And if we take a look to the number, we may notice that just the growth of the plant sequesters from the atmosphere 1,390 kilograms of CO2 per ton of fiber each year. Talking about the thermoplastic resin right now, here we have a pie chart. Unfortunately, we were not allowed to share with you the percentages, but to give you an idea, if we have a composite made with thermoplastic resin and the dry fiber, and we want to recycle it, we will recover more than 40% of the dry fiber itself. Then there's still a percentage of recovered crude oil, which can be reused to produce thermoplastic resin again. Another percentage of gas, and the gas can be used to recover some energy, and unfortunately a very small amount of solid residues. Now, if you take a look to the bar charts, here you can find a comparison between the environmental impact of our new cockpit made in flex fiber and thermoplastic resin compared to our last year cockpit made of carbon fiber. And you can notice how the impact is drastically reduced.
So this year we had the opportunity to partnership with Curti, which is a leading manufacturer of composite components based in Emilia-Romagna. They offered us the possibility to use some of their expired carbon fiber, and we accepted, and we used it to make some crucial components of this year Futura, such as the pilot seat and the battery box. Speaking of CFRP, which stands for carbon fiber reinforced polymers, we have to know that there are some drawbacks. Talking in numbers, 85% is the percentage of obsolete component which goes directly to the landfill without getting a proper recyclement. 1% is the degradation of the CFRP over 100 years, and 2,000 are the kilograms of CO2 that need to be emitted to incinerate just a single ton of CFRP. So, knowing this, we had to do something. So our commitment was to find a way to manage the end of life of our obsolete component and our scraps. We find a possibility and an opportunity by partnership with Fiber, which is a new astonishing project based in Emilia-Romagna, partnership with ERA, which manages the end of life of composites component. The process they follow is pretty much this one. It's articulated in several steps, but the crucial one are the pyrolysis and the gasification. It all starts by collecting the scraps and the obsolete components by teams such as Uniboat, but also Uniboat Motorsport, and then they get heated up. After they be heated up, the resin simply gasifies, and leaving only the dry fiber, which could be recovered. During this process, there is the production of a lot of fumes, a lot of hot fumes that are used to keep the oven hot and spare some energy. So, knowing this, we planned to remake our hulls, because last year we had a pretty big project, which was to make our custom hulls based on the one that the Yacht Club of Monaco offers us every year. And we have a rough estimation of the weights. 150 kilograms for the hull's mold, 140 kilograms for the hulls by himself, the old cockpit of 6 kilograms, and the old outboard engine strut of 4 kilograms. That sum up to around 300 kilograms of obsolete composites component that, with the process that Fiber is able to offering us, we were able to recover up to 150 kilograms of recovered carbon fiber. Watching carefully to the right, we can see the pie chart in which we have the 50% of recovered carbon fiber, but also a 46% of recovered resin. We should not consider it as recovered, because we do not get any material by this process. We get energy. We save energy and spare some energy. And of course, we have a 4% of waste that unfortunately we are not able to avoid. So keep going on by planning. We decided to see how we could reduce the impact on remaking our hulls using recycled carbon fiber. On the left, we can see a bar chart in which we have a comparison of the recycled hulls mold and the hulls mold made with virgin carbon fiber. Using recycled carbon fiber, we are able to recover up to 80% of our carbon footprint in terms of fossil material, and 66% in terms of non-fossil. Thanks for your attention.
I think this is on. Yeah, thank you for that presentation. That was really great to see some of the work that you guys are putting in. I've got a quick question, and then I'll see if anybody else has one for you as well. But I was wondering, once you'd rebuilt your whole vessel, you got your final footprint, what at the end of that project is now your biggest concern in terms of environmental impact? So you've looked at last year's, made lots of changes, lots of improvements, but based on what you've got this year, what would you say is going to be the next thing that you need to try and solve? I don't expect you to have a solution, but what would you like to see in the future?
For sure, one thing on which we have to work about is like to rebuild better the battery box. Maybe the battery box is one of the components in which we can work on renewable fabrics, such as the flax fiber, because it's not subjected to that much of structural loads.
Perfect, thank you. Does anyone else up here have a question? Otherwise, I've got another one.
On the process, using flax and recycled carbon, have you noticed that this material absorbs more resin than the new one?
Well, to be honest, there was not much that different. They are still very valid solutions, and I have to say, by our experience, we suggest the use of this type of solutions.
Okay. I've got another quick question. Yeah, as you mentioned, that you've been using expired carbon fiber and also the reclaimed carbon fiber. What kind of challenges did you have working with those materials, if any?
Well, as I previously said, there is no change in the performance, and the use of this type of fiber, so the expired carbon fiber, really has no difference from using not expired carbon fiber. So it's a very valid solution for the reduce of the waste.
Amazing.
Yes, so I think you have monitored all the results of the life cycle analysis on the Marine Shift 360. So I guess you try to optimize the way you come to Monaco in order to reduce the footprint, etc. But as we have some people from the industry in the room, could you please share? It looks like it's quite easy, simple, cheap. Not cheap, we're not sure, but we need to have some ideas. If you can give advice to the industry to try to reuse such solution, because if they want to build a boat, that might be a good option. So could you share some, as we asked before, the biggest mistake you have done, the good idea? It looked like for you it's natural. If you have to build a boat tomorrow, you will use this technology. So we just need to share with the room here what's, after this experience, your advice, the mistake, and the experience you can share with everyone in the room.
So, one of the biggest challenge as a student who tries to approach as a lamination approach is the fact that currently you have no idea of what you're doing. You basically have someone that tells you you should push correctly on the edges and something like that. So the thing that I would like to suggest to not maybe the industry, but the people who are listening to us is to take the current information, try to follow and be taught by someone who is really, really an experienced worker on the sector.
That's a good advice. Thank you. No more question. Congratulations.
Thank you, Uniboat, for this presentation. We can now move on to another finalist of the Innovation Prize, this one being Elettra UniGe.
Telecomando. Okay. Okay. Hi everyone. We are Team Elettra from the University of Genoa, and today we are presenting a convertible outboard transmission for single and dual propeller configuration. In today's outboard market, a user must choose between single or counter-rotating, but this choice, he must choose between two different setups. The single one, which is ideal for low speed, denoise, and it can be more efficient in low load conditions. And on the other side, we have the counter-rotating one, which delivers more thrust, better control, and fast accelerations. But, however, this trade-off limits both versatility and also the okay. No. No. Okay. Thank you. So our solution is an hybrid transmission, which is convertible from the single configuration to the counter-rotating ones. This is possible thanks to a modular design, which consists in removing the inner shaft and replacing with an intermediate component, and also removing the related components. This thanks to this feature, it's possible to use the same hardware architecture and adapt the transmission to different uses. In fact, one of the main features of this project is that we can have two different transmissions without the construction of two physical objects, and at the same time we improve the management of spare parts and maintenance, because the two different configurations almost share the same mechanical architecture. On the operational point of view, we obtain a single propulsion platform that can be adapted to different navigation conditions and also to different mission profiles. And also the energy consumption can be optimized in function of the load requirement. In fact, the single propeller configuration can be more efficient, for example, in low load conditions than the counter-rotating ones. So the single propeller configuration is ideal for low cruising missions, low speed cruising, and sustainable tourism, because is quieter than the counter-rotating one, and so is ideal for example, for the navigation in marine protected areas, in order to reduce the noise on marine wildlife. While in the counter-rotating one is always better when we required high performances, so high thrust, even with small diameter propellers, and when in general we need also accelerations and better control.
Okay, I'm Enrico, and I'm another member of Team Elettra. I work on propellers. I want to start with our propeller design approach. We have different steps. First step is setting input data. Then we have design method. We use some open source code that we modified in order to adapt them to our application. And finally, we have an adaptation of our geometry to 3D printing and composite materials. Starting from an hydrodynamic focus, we can say we use a lifting surface method to design our propellers that enables controls over chord and span in order to find the optimal distribution of pitch and camber over the blade. Then that's the part about adaptation for 3D printing. As you can see, we have to add a little bit of thick on the trailing edge of our sections in order to make them printable without the risk of delamination. And we do some other tricks in order to make our propellers printed by 3D printing and to make them solid because we use composite materials and not steel. Then we have the validation part in which we study and validate our results. We evaluate an open load diagram, open water diagram for our propeller that then we match with our motor. Our results are also validated with testing in the cavitation tunnel in our university, and that part is really useful because we use the cavitation tunnel to optimize our CFD in order to have a more efficient process and quicker process. Then
this year's decision to build the drivetrain from scratch gave us greater freedom when selecting the motor for Elettra. The chosen motor was a 3-phase permanent magnet synchronous motor with a rated power of 10 kilowatts. And to test the full capabilities of this motor, we used the following setup. Two motors were acquired along a pair with inverters, and the shafts of the two machines were coupled, forcing them to rotate together. And the DC buses of the inverters were put in parallel, both fed by the same voltage source. During operation, one of the machines acted as a motor, and the other as a generator. In this way, by this configuration, a closed energy loop is formed, and the external voltage source only needs to supply the amount of power that corresponds to the losses in this closed system. In this way, we were able to push the single motor to high torques and high currents, which are representative of operational use, but without having a full-scale power supply capable of supplying that full power. The results are shown in the graphs. Moreover, by measuring the power output of the voltage source, we were able to estimate the losses and thus estimate the efficiency of the inverter and motor system, which range from around 70% at lower speeds up to 90% at higher speeds where the motor is designed to operate. Thank you for your attention.
Well, congratulations, because don't be stressed. We are in a big family, it's okay. Look, do we have some questions in the jury in the room? Okay, sorry, pardon.
Hello, congratulations for your presentation. A quick question, can you explain how you switch from one mode to the other, and how easy it is for a user or client to do this switch?
Yes, allora, we remove the, at first, the lower unit of our transmission is composed by different closures. And opening one of them, we are able to remove the inner shaft, also along with bearings and all components, also the rod seals, for example. And we close the external one in order to prevent the water to enter inside the transmission. And this allows us to switch from a counter-rotating configuration to a single propeller one.
Okay, so it's not something that a standard person using your technology would be doing. It's like something that is done by a technical team, right? Yeah.
Yes.
Okay, thank you very much.
Thank you. That was very connected with my question. You know, in the innovation prize, we need to know if it's innovative. It is innovative because we don't have no many teams doing that. We have few teams. But it is true that might be a need for the industry, maybe because we know that some propellers are not very efficient. So if you can come on the market and say, okay, look, I can offer a shaft that can go on every kind of engine, from Suzuki, Yamaha, or Mercury, or whatever, all the normal engine. And by using our innovation, they can increase the efficiency and have a real impact into the industry. It's a bit what is missing in your presentation. You know, as a jury, we need to understand, okay, what will be the real impact of your innovation? What's the way you want us to put you in the world, to give you the opportunity to create something? I need to feel that.
Yes, for example, if I know that I want to go in, for example, in a marine restricted area, I can put the single propeller version in order to reduce, for example, the noise on the impact of noise on marine wildlife. While if I want to have fun in open sea, I can mount the counter-rotating version and push as I can.
Okay, but I need to know how many times, what's the price, what's the market, you know? we need to feel that.
Yes, for example, an industry of outboard motor can solve the counter-rotating version, and in a second moment, the conversion to pass from the counter-rotating one to the single one. And it's a philosophy that we find also in some sports like shooting, like Olympics, where they sell you a caliber, and you can convert to another in order to change competition.
Grazie mille. Thank you so much.
Thank you, Elettra, for this presentation. Now moving on to our second finalist of the Design Prize, I would like to welcome Adria Racing to the stage.
Good afternoon, everyone. My name is Ilona, and today with me is my colleague Martin, and we will present to you our design for this year's Design Prize. Firstly, I'd like to tell you a little bit about us, where we come from. So we're coming from the city of Rijeka. Rijeka is Croatia's principal seaport. It's situated on Kvarner Bay. Our city has a rich history of maritime, and you can say that shipbuilding is etched in our genes, and that is a good reason behind that. As you can see by the map, city of Rijeka has a good geographical location. It was, in the last 150 years, a central port for whole Europe. We like to joke that under the different situation, and if history has arranged a little bit differently, Rijeka would have been a Mediterranean Monaco, since we were in the last 150 years under as many as 7 different countries. And a little bit about us. So we are the Association of Applied Technical Sciences. It's a part-student project with cooperation of the Faculty of Maritime Studies and the Faculty of Engineering, which was founded 7 years ago. And we are based on modern technology and eco-friendly problem solving, emphasizing why it's important to be responsible. This is just part of our team, a group of students, engineers, and professors from University of Rijeka. There are many more, which I would like to take this opportunity to thank, because without them, this whole journey wouldn't be possible. But let's talk about design, the thing we are here about. So the inspiration for our design comes from the torpedo. If you don't already know, torpedo is an underwater missile. It has its own guidance, directions, and for directions and depth, and it was developed in the city of Rijeka by the Austrian naval Ivan Blaž Lupis, and it was the inspiration for the cockpit of the boat. Now I will give the word to Martin, and he will talk to you more about the design.
Thank you. So, for the design of the cockpit, we had 3 things in mind. So, we want to make it aerodynamic, lightweight, and of course, it has to look good. So, to make it aerodynamic, we made an enclosed cockpit all the way to the back. So, the battery and electronics are in the back, and the pilot in the front, separated by a fireproof bulkhead. So, to make it lightweight, we had to add, to make it lightweight, we used 2 carbon fiber beams as a base. So on those carbon fiber beams is the pilot seat, the battery, and the motor. The rest of the cockpit is made from single laminate skin carbon fiber, only reinforced with sandwich in a few parts around the pilot. So it's very lightweight and made with a lot of radiuses in the front, going all the way through the back. So only with the inclusion of the bulkhead, it gives it enough structural integrity to hold the steering, the steering gear, and it's also made so that the pilot is strong enough so when the pilot comes out it doesn't fold. So it's made with single laminate skin with no other structural pieces to hold it together. Next, we designed and manufactured our own steering wheels. So we made two designs. One is inspired by Formula One, so that's the right design, and the other is inspired by our last year's steering wheel that we bought, and we figured that it's hard for the pilot to steer with one hand and use the gas with the other, so we add a little knob, rotating knob to steer the boat. And so this year design, one is with two knobs for easier maneuvering, and the other one is Formula One inspired. And also we added a quick release so we can easily change the two different wheels. Next, we bought a seat. So it's a go-kart seat. We put it on our AI boat, but for this one, we 3D scanned it, put it in software, made it a little bit smaller for our smaller pilot, made the mounts, and made it from fiberglass. Next up is the battery pack, also designed and manufactured by us. So it's a custom battery, so it's 28 series, 20 parallels, so it's 98 volts. It uses Samsung 50S cells, 560 of them. The casing is glass fiber, and it's also water-cooled. Right here, the water cooling system is not in the picture, but it also was designed and made by us. It was 3D printed, and you can come check it out later. In my opinion, it looks good. Next up, we have the motor mount. It's also made fully from carbon fiber, also designed and manufactured by us. So we used pre-preg to make the tubes, and we used the infusion to make other components, which were then water jet cut to make the whole structure, which then was assembled and laminated together to make it strong. Next up are the propeller designs. So this year we wanted to make our own propellers. We used OpenProp and MATLAB for it. We made around 10 propellers for our boat, and we tested them, but we had some issues with manufacturing, with time mostly. So we then got the top speed one, which was then pretty good for endurance also. So we just used the top speed one, but we'll continue researching and testing these propellers so we can make one for endurance for next year that will be much better. These are some of the softwares we used for the design. So Maxur for design and calculation, speed calculation, modeling, all 3D modeling was made in SolidWorks, and propellers were made with MATLAB and OpenProp. This is our electronic scheme. So we have a 96-volt battery. We have our engine, which is 20 to 25 kilowatts, communication for the engine. We have the telemetry system, and we also put in the solar system, but we are unfortunately not using it this year, but for next year we'll make it work. And before I give my word back to my colleague, I'd like to say that I'm very proud that we made the whole boat, besides the motor, the beams, and the steering system, which is hydraulic, all by ourselves. So we designed and manufactured everything in-house, so 10 to 15 students made everything. So yeah, thank you.
And just at the end, I'd like to discuss our visual identity, which was inspired by the elements of the Croatian flag, and the special emphasis was put on the red checkerboards, because if you know Croatia by something, you know them by red checkerboards. And our design reflects the national pride and identity through modern and dynamic visual language. And this is our last year's picture of the boat, but I invite you all to come to Paddock and see this year's boat. Thank you.
Are there any questions?
In the audience? No. Thank you for your presentation. Just one question. You said you've been inspired by the torpedo design. In which way I can find the torpedo into your, say, fuselage, because it's all along the boat, which, on the other hand, I found very attractive. But I do not see clearly the relation between the two.
It was inspired, so it's long and narrow, and it also it resembles a little bit. It also looks a little bit like a bullet or something. So in that way, it resembles. So it goes. It's fully enclosed, so it's one structure, and that's what kind of we went for, and that was our inspiration.
Okay. Now, because the shape of torpedo is very simplest, with a circular section all along, and your fuselage is much more complex. So that I wanted to understand the process from the torpedo shape to...
We wanted... we started with the torpedo design, and then, as I said, we wanted to make it lightweight, so we had to add a lot of radiuses to it, so it can be self-supporting without any other structural components like ribs. So we started with the torpedo and ended up with our concept.
Thank you. That's exactly the kind of information that would be interesting to have into the presentation, to understand how from a torpedo shape you end up to this shape.
Okay.
Thank you.
Thank you.
Sean, you have used epoxy fire retardant. How was your experience in using this material? You advise others to use?
We did a lot of vacuum infusions in the past, and we just followed the instructions, and it worked. Any more questions? Thank you, everyone.
Thank you. Thank you, Adria, for this once again amazing presentation. Moving on to eco-conception prizes, I would now like to welcome Messina Energy Boat to the stage, please.
Hi everyone, I'm Vittorio Geraci, the head of the design group of our team. Today I'm here to talk about a story made of professors, PhD students, and students of the University of Messina that faced the challenge to make a competitive boat with the lowest carbon footprint in the race. As I said, a few words about Messina. Messina is in the middle of the Mediterranean. We have a strait that has a big marine traffic. We see a lot of traffic that comes out of our windows. But let's dive in. Our philosophy. We've started designing this boat by analyzing a lot of data from the whole boat, the boat from the last year, and to analyze a lot of data from a lot of simulation that we ran during this month of designing. As you can see, the last point tells us a mobile laboratory. In fact, we want to prolongate the life of our boat to collect data in the Strait of Messina. But let's dive in the design phase. When we started to design the boat, we ended up in a loop, a continuous loop of data coming from marine shift, coming from fee analysis, and from other analysis that we have done. And this is our loop. We have analyzed different kinds of structures in different materials, and we interpreted the results. We've run other simulations, and we ended up with the boat that you can see in the paddock. This is our first simulation. This is a comparison between 3 different kinds of structure. You can see a carbon fiber structure, an aluminum one, and a wooden one. And as you can see, aluminum has the lowest carbon footprint. That is nice, not only for the competition, but in general, you can apply this to every structure in the industry. The aims, as I said, of this boat is not only the competition, but is also to collect data in the Strait of Messina. Not data coming all from the boat, but also from the environment to implement some solution on our strait. When we've considered the carbon footprint of our boat, we considered every aspect. I'm saying every aspect. Also the logistics one, that is the trip that the boat has to do to come here, and also the crew and the members of the teams. And we read a lot of articles about different transportation methods, but we will come there later. As I said, we used aluminum. Maybe someone in the industry can say that we have done with steels and alloy structure. We don't have any improvements to do, but it's not true. We've made a lot of progress in this field. We can make better structure that is in aluminum or steel, and this structure is completely reusable. I'm not saying to melt them, but we can reuse some structure and completely reuse them. We've used in our boat only aluminum. It's all made of aluminum, 7000. And we use this technology that is aluminum honeycomb sandwich. That is one of the fields that our university is researching to. This is the main scope. I said that we've looked to everything, and this is maybe anything, everything. The design phase in our university, the production of every single component of the boat, and the life of the boat at sea. So when the boat is in the water, what is his carbon footprint. We considered a phase of navigation by like 3 months in the water over a year. I said everything, and this is the logistic part. So where what we've considered to evaluate the carbon footprint of the transportation of the boat and the team itself. This chart is another comparison. It's a comparison of different types of transportation methods, and as you can see, the train has the lowest carbon footprint. You can also enjoy more the trip, maybe. You have a lot of comforts, so choose the train, please, to get somewhere. we've reached our goal. Yeah, we've reached it. And we've made a boat that is fully reusable. It's fully integrated with the university also, because we're doing research on that, on the data that we are collecting on that boat. And this is the final chart, the chart that shows us how all the components have an impact on the general carbon footprint of the boat. As you can see, if you do some maths, the 60–70% of the carbon emission of our boat is related to the electrical components. But we are reusing it, so we don't throw the batteries away, but we reuse it to give power to some instruments at the universities or in the boat itself when we collect data. This is a different way to see the chart that we've seen in the last slide. And this put us the three phases of this boat. So the production that obviously makes more carbon emissions. The use phase that depends only on the charge and discharge of the battery when we use the boat, and the end of life. You can see the tower of the end of life. It's really, really small because we, as I said, we reuse the boat. We use it to different aims, and she's never die. Maybe we can say it like that.
Hello to everybody. My name is Giovanni. I'm here to explain you our research about vibrations, because our boat was used to test and to investigate ships' vibrations. So our prototype was equipped with some accelerometers, strain gauges, with our digital acquisition system to correlate this data in real time, making some trials in the Strait of Messina. Because each structure has got modal parameters that we want to identify, like resonance frequencies, damping, and mode shapes. Our goal is to find them in a big structure without using some laboratory tools, because you know, for finding out model parameters in a structure, you have to use laboratory tools like hammers and everything. So our goal is to find them directly, making operational model analysis. So you can say where we put accelerometers on board, record some signals, and compare it with our finite element model to assess their values. So here you can see some results of the finite element analysis and the experimental model analysis. You can see that there is a good, there is no divergences, but we are making this test because our idea is, if we got a big ship, okay, we want to know model parameters of these ships in order to improve the structural health monitoring of it. It's important to develop a system in real time that gives us these parameters and not analyzing every single structure into a laboratory, okay? We are trying to develop this system and this procedure in our laboratory. Okay, here you can see some pictures, videos about digital acquisition system on board, accelerations, signals that are useful to decouple model engine behavior and propeller behavior from the structural one. So signal analysis processes operations that are conducting in our sea area. You can see here our boat sailing, okay? And validating this data also using strain gauges for the strains too. Thanks for the attention.
Thank you so much for that presentation. It was really great. Quick question from me from the beginning is, you've put a lot of work into really understanding the different materials and looking for a different approach to building that's going to give you a lower impact. Were there any areas that you looked into that you couldn't find a solution that you'd like to see a better solution in the market?
So we think that the alloys, that aluminum in particular, is the best solution to build structures at sea. It does get rust, so at least it gets rust really light, and it's a very good solution. Maybe it's more difficult to manufacture because you need weldings, you need to bend it, you start from some sheets that you have to work on that, but it's the best solution, we think. We can also look for some composites, but in Messina it's easier to make alloys, to work on alloys. Maybe for the next years we will have some parts made of composites, but we have to reach that same footprint because we can't get higher.
No, that makes perfect sense. Any other questions?
I saw that you made the comparison on the CO2 footprint basically after production in order to get the boat here, right? But in the 3 examples that you put up, I missed the shipping. You put like train, plane.
Okay, and it's there.
Yeah, car, train, plane. So from Messina, maybe you could also have put it on a ferry.
Yeah, but it's referred to our the trip of the people, of the members of the teams. So obviously the boat took a ferry to get here, but we took a train because it's better. We can't put the boat on a train.
Okay, well, okay. Choices. One more comment on sustainability. Rightly so, we talk many times on CO2, right? But there's also many other aspects on sustainability and impact on the ocean environment, and one of them is also acoustics. I know it's a really small boat, small propeller, but still there is an impact. So maybe just put a thought for the future.
We've done a lot of research. As I said, we're using this boat as a mobile laboratory. So we are taking not only data from the structure or from the electrical components of the boat, but we are taking data also from the environment around the boat. And we measure the carbon emissions on the strait and also the acoustic pollution inside the water. Maybe an electric boat obviously gets less noises in the sea, but with all the species that lives in Messina that cross the strait every day, we have to keep an eye on it, obviously.
Absolutely. Thank you.
On a similar question, in terms of a more holistic approach, did you find that by moving towards aluminium, because it was beneficial from a carbon perspective, that on any of those decisions that you had areas where you maybe had higher impact in another area, for example, mineral resource scarcity or energy use, water use, did you find that by selecting for carbon that you are potentially finding higher impact in other areas?
So, in our area, it's easier to get alloys, as I said. In other area, maybe it's easier to get composites, but the production is the part that emits more CO2 in the air, has a bigger footprint. So that's maybe a question that you have to put it in I don't know how to say it, but it's like you have to consider different factors of different fields, not only an engineering field, but also a logistic one, and maybe also a lawyer one. And yeah, maybe aluminum is the best solution. I have to talk maybe with someone that worked on a boat with composites, and maybe we compare that, but I didn't done that. And yeah, we've made the analysis with marine shift, and yeah, we've tried also different producers, different companies to see how the trip of the materials impact on the final product, and we find that in our location it's better to use alloys.
No, that's great. That definitely answers my question. I think the difficulty is that there is no perfect solution for anyone at the moment. There's always going to be trade-offs. And what's really interesting to see is not just that you've chosen aluminium, but why you've chosen it. I think that you've shown at the beginning the comparison from a carbon footprint perspective of the difference between the carbon or the composite various materials. It's also just really interesting to see what other factors went into that decision making. So performance, obviously, is one of them as well.
Yeah.
But yeah, and location as well. So yeah, thank you for explaining that.
If I can say it's about the performance of the boat with aluminium and the difference between aluminium and carbon fiber, we've seen that there's not a lot of differences in terms of weight. We implemented the weight of the boat by 13 kilos.
Thank you.
Thank you, Messina, for presenting your sustainable approach to us. Now I would like to move on to our third finalist of the Innovation Prize. And right after that, we will take a coffee break. So could I please have you, Antwerp, on the stage?
Yes. Hello everybody, I am Jonas and this is Lucas from the Antwerp solar boat team, and we will tell you about how we converted our solar powered boat to a fully autonomous boat. First, we're going to tell you something more about general information, about the team and everything. Then we're going to divide the approach that we also did in the team ourselves, because it was a big mission, and to make it a bit more easy, we divided it in smaller parts, and then the current state and the future progress in everything. So first, we're a student team that is from Antwerp in Belgium. And we only consist of students that do our thesis, master thesis or bachelor thesis with the team, and we are roughly 15 people.
As Jonas mentioned, we divided the project in smaller projects. These are the small projects. The first project that we start with is the obstacle detection with AI. We recognize buoys and other boats and point it on a map so the boat cannot drive through the other objects. After that, we worked on the pathfinding. The pathfinding points on a map waypoints, and we navigate through the waypoints. For that, we also need accurate navigation, because the AI has to know where the boat is on the map. These were all the AI parts, but for the translation, the waypoints and the velocity translated to the auxiliary throttle of the motor, we had an automatic control system and a steer-by-wire system. And also we have a lot of safety measures in the boat. to approach the waypoints, the pathfinding, we used ArduPilot. ArduPilot is an open source platform that's also used in industrial and professional context. It's open source, and there is a lot of documentary because we have to start from zero knowledge about AI and pathfinding. So it was easy to use an open source platform. And we also documentary everything very good, so the next team members don't have to start from zero again. Then for the object detection, and we are using AI. We are using the YOLO 11. YOLO 11 is the newest version of the you only look once. To see, we use 2 stereo cameras. Each stereo camera is made out of 2 cameras, so we can see in depth. And then this data is sent to the Jetson, and the Jetson is the computer that recognizes the buoys and the other boats. Here you see a video of the AI working. The pilot is driving manually. It's only to test the camera detection, and as you see, it's working quite good. For the navigation, we pointed waypoints on the map, but because of these waypoints, they are a little bit pointy and not a smooth path. We use an algorithm that smoothens out the path, and the boat can go fast in during the race. Also, the AI recognition points out fences on the map where the boat cannot drive through. The fences are pointed in red on the map. As I told in the beginning, the waypoints and the velocity has to be translated into an actually signal to the motor controller and the PLC system for the steer-by-wire system. This is done by this curve. So in the beginning, we have waypoints. These waypoints are translated to a position, into a velocity and an acceleration. And then we go on to the steer-by-wire system.
So now we know where we want to drive. Now we actually have to drive the boat itself, and this is really important because at last year we only had a wire that was from the steering wheel to the actual motor itself. So we had to switch it because an AI cannot steer just by actual force if it doesn't have a motor. So we switched it and gave it a motor, and there were 2 options. There was the steer-by-wire and the electronic power steering system. We chose the steer-by-wire because it has a lot more positive attributions than negative, only the higher costs. But when you integrate it good and fully, the positives are much higher than the negative. We also featured a safety aspect to everything, because as you can see, we have 2 inputs. There is a Pixar 6X, and this is the AI itself. And then there is also the person, and this is the pilot, of course. The pilot itself steers by the steering wheel, and it translates, it gives a signal to the actual motor that gives the direction to the steering wheel and everything. And if you want to go fully autonomous, it is easy to switch with the switch. And that is also the safety, because if we are driving autonomous and there is a problem, the pilot can just steer harder than the motor that is driven by the Pixar, and then the pilot takes over and it isn't autonomous anymore. To make it a bit more to make it future-proof and everything, we switched some things around. And the biggest difference is that here is no feedback to the actual pig's hawk. This is because you don't want an extra resistance for the motor. It isn't necessary, and it is nice to have a resistance for the pilot itself. Otherwise, it is too easy to switch everything around and to steer actually to the wrong point. Then there is the fully safety part. This is really important because if not everything is true, then the boat just doesn't drive on its own and the boat stops. If this happens, the boat will actually reset and start it again. And if it keeps failing, then we have to come back and look what the bigger problem is.
We believe that with our project, we have proven that there is a lot of future potential. Not for big boats, but for semi-small autonomous boats. I think we have proven that it's possible to go to work further in this project and made some autonomous boats. It's not good for larger ships because there are more motors. The steering is more difficult, but it's possible with smaller boats. Thank you for your attention.
Thank you, gentlemen, and congratulations, because yesterday you were the first performing the AI class without default from the first time, so that's amazing result for the first time. Do we have some questions in the jury or in the room? Okay, as usual. Pardon, vas-y.
So thank you for the presentation. A question, so you did your first racings yesterday. Could you share with us how it went and if you saw any improvement points or if you learned anything during the races? Could you share this with us, please?
So it went pretty well, actually. We were able to identify all the buoyings with the AI itself, so we didn't have to set any points ourselves. It was fully autonomous, but the biggest part that we wanted to change, but we didn't have enough time, was the radius that we went around every buoying and the quickness of the boat itself. It wasn't on full throttle the whole time, but we could switch some parameters that it could have even went faster, but the time was just limited, and we didn't want it to crash into anything or anyone, to be sure and safe.
Good insurance.
Thank you.
Thank you. So I think it's something very important for all the new generation arriving. Could you please share 3 points? The first one is the AI learning. I understood that you were looking for AI code that was self-learning. So could you please explain a bit more in details why you chose this one, not another one? And basically, you can orient the lessons learned from this AI. So how do you proceed? And could you explain in which hardware do you implement it in order to have not a maximum of limitation?
We chose the AI because it is open source and it was free. So to reduce the cost itself, we chose that one. And to learn everything to the AI, we just used pictures and we went and set like we pointed out the buoy itself manually, and we gave it like 15,000 pictures, and we all did it manually to learn how buoyings look and how they can change when the sea is forming and everything. Then I am lost. What was the next question?
Now, the hardware. What kind of hardware did you choose to implement this?
We use the Jetson to put everything on its as a computer itself.
Thank you. Second question. So for all the team here, if they want to go through AI, it looked like having some movies and video about what they are doing this year might be a good help.
Excuse me, I didn't...
Having a movie about what they are doing this year with the boat might be a good help for the AI to have the lessons learned.
Ah, yeah, true. Yeah.
Okay. Second point, in your graph, PDI, I did not see an accelerator, GPS, to know where you have the limit, because your boat is foiling or not. I do not understand that.
At what point, or is it this one that you meant?
Yeah, I do not. I think is your boat a foiling boat, correct?
No, our boat isn't foiling at the moment. It's just that was last year we tried it, but yeah, the foiling itself was a challenge, and now the AI was a bigger challenge, so we chose the AI.
Okay. How do you limit the G curve on the maximum speed to the AI in order not to be in too risky mode?
We used a PID controller. It gives a maximum value, and it will overshoot or undershoot it, and it will change the direction. If you go too fast, it will give a back throttle, and then it will go, if there is a baseline, you go really fast or slower to your set point, and then you go over or you go lower, and then you will change everything.
And the maximum velocity and acceleration is pointed out in ArduPilot. It's a setting in ArduPilot where you can say the maximum velocity is 5 meters per second, or faster or slower. In the beginning, we did it slow, and then during the tests, we can put it higher or faster.
Thank you. And last question, do you use some ChatGPT or other AI to improve your own coding inside the other AI?
Yeah, we did, because we are students, and especially we are electromechanics students, not computer scientists. So the coding was very hard for us to do and to learn. But thankfully, we used ChatGPT and other coding AIs.
I felt that, huh?
Yeah, but it was mostly for correcting it. Writing itself, it isn't that far yet. It's more, this is the code that we want to use, but there is a problem. This is the error we got, and then it can change it. That's better to use it than just write this. It doesn't work at all.
Don't worry, we all use it now.
No, but it's just for other people listening.
Okay, and we have another question.
Thank you very much for your presentation. I will need some more detail concerning this solar power. When there's no sun, how do you do?
Fully powered, and then we go onto the water, and when we use our battery itself, it will recharge with the solar panels that we use. But at this moment, to make sure everything is safe, we don't use the full efficiency and full power of the full battery. So most of the time our battery is almost full.
And one last question for the jury. You know that for the innovation prize which we are attempting, it's important for us to know what is the impact of this proof of concept, the scalability. So could you give us an idea about, okay, you see this innovation will be needed, or is a need for which kind of application, what kind of matter it will solve, and how do you see your innovation is helping the world of the marine industry? We need to understand that a bit better to give you the correct graduation.
Okay, to implement it in boats that are not the big yachts but the smaller yachts, that is pretty easy because our boat is also quite long and big, and it is for autonomous driving, not particularly inside the harbor. It's not there yet, but outside and in the sea it is good, and it will detect the buoyancy in the other boats, so it can navigate through without a pilot, without a captain, without a captain that is driving the ship itself, so it can be replaced with an AI.
Thank you so much, gentlemen. Ladies and gentlemen, could you please come back on stage? We know that having some coffee break is okay, but please consider that we will have some long deliberation after, and the more we can respect the schedule, the better it will be for all of us. So could you please be quiet, the ones that want to continue to have some glass? All the other one, if we can start, it's cool. Thank you.
So in this second half of this edition of the 2025 Tech Talks, I would like to welcome Physis Polymer Energy Boat for the Design Prize.
Hello, everybody. My name is Morena. I am the Marketing Unit Coordinator at Physis PEB, and today I have the honor and pleasure of presenting you Nidra, our concept, our challenge, and our creation. After 3 years participating with the same name, Yone, we finally got another name. Here is Nidra. Nidra aimed to convey the meaning of hydrodynamic. And I would like to open my speech with this statement that resumes the aim of this project. Nidra is engineered with precision and shaped by the waves. Looking at the index, here we went through 3 different phases. The first one was the concept phase, in which we arrived with a long part of research and then briefing. And then we reached the design phase, the most hard one, in which we finally designed the shapes and the architecture of our cockpit. Then we finalized everything with colors, materials, and textures. Looking at the concept phase, here we have one mood board that is not only a visual description and information, but it is also a kind of reminder of 3 different inspirations. The first one is the motion of propellers and the natural wave of the sea. And then here we have the carbon fiber that is central in our design. And our third inspiration, the racing universe. In fact, we really wanted to bring onto water the propulsion and the speed that usually we can see only on 4 wheels. Here we pick from the inspiration the first sketches that brought us to 3 different shapes. The first one, the air intakes that were adapted to the nautical world, but still keep a reference with the racing world. Then here we have the FC shell that aim to represent the speed and the propulsion through waves. And here is our dashboard that is a way of protecting our communication with the pilot. Here we go through the design phase. Here there's an overall design of our cockpit and 3 different parameters. The user interface, material, that is carbon fiber, and then delivery, the visual identity of Physis PEB and our boat, Nidra. Talking about the user interface, here we have our dashboard. We aim to convey efficiency while speaking with our pilot by land. And then talking about the main features of this dashboard, here we have the graphic design we designed the graphic trying to highlight colors and also symbols that will be easily recognizable by the pilot. And then we analyzed 3 key points and key information for the pilot during racing conditions. The motor state, that is very important and crucial during the race. Logger, that aim to alert the pilot in danger conditions. And also the battery life, that aim to communicate to the pilot the status of our battery during the race. Talking about the second part of our design, we went through the material, and this part is the one that we really wanted to be engineered with precision. In fact, we chose carbon fiber because of its high performances and lightweight structure and durability. Why we really chose carbon fiber? First of all, because of its pattern and its visual effect, but also because of its durability through times that helps us to reuse each part of our boat. And then because of the fact that carbon fiber helps us to create shapes that in normal conditions could be hard to create. Talking about the third part of our design, we went through the livery. That is the part that we really wanted to seem to be shaped by the waves. We analyzed the livery that brings together the performance and identity of Physis and of Nidra. And beyond the livery, there is the propeller motion that inspired us, the curves that we introduced in our cockpit, and also the visual identity through one color that is fuchsia, and it is highlighted by silver lines, mixed with one other color that is the red of our main sponsor and supporter, Chiaravalli Group. Here we go through the final design. There's a visualization of our overall architecture of the cockpit, and then few details that highlight the harsh shapes mixed with curves and convey the sense of our design. Here there is our Nidra with its colors and textures, and we finalize it with our main supporters, partners, and our university, Politecnico di Milano, together with the 2 departments that supported us through our journey, and also our roots, the Italian flag, and 1 lucky number, the 23. Nidra, it's so more than a boat. It's our commitment, our teamwork, and Nidra has the aim to set the lines of our design on water and in our story. So thank you from Physis, and thank you for your attention.
Any question in the audience? No. I have one. Can you explain a bit more about the relation between the shape of, for example, the air intake with the technical parts inside the boat? So how the exterior shapes improves some parts of the technical
Yeah, sure. At the very first time, we reused our last here cockpit, and we improved it along with the concept that, as I explained, was taken from the racing world. And in this case, we try to design that parts in terms of speed and aerodynamics. So that's the effort that that part puts into the design overall.
Now that's the part which is interesting in design, is how you connect with the technical requirements or improvement that you want to make, and how much those shapes involves the results or the improvements, the technical improvements inside.
Yeah, well, the technical improvement is has a lot to do with the speed, because of a shape that is, as I said, very aerodynamic, so that easily can go faster than shapes that were taken from last year and were very harsh and not that curved. And that's why we wanted to introduce the shaped by the waves.
I'm sure of these results, but it would be nice to see them by CFD or whatever means to explain with proper numbers. I mean, as engineers, and that's the first time that we have such a presentation where there is no graphics, no results, and very nice for the design, but the design is global, so you need to make the link and see how the design, the exterior shapes influence the results. So at this point, this is the missing part of your presentation, and how you connect with some results or some improvement in
well,
your
yes,
bot.
I understand.
I'm here not trying to, I mean, it's for all the audience and for all the teams, how to improve your presentation, and how, as designers, we make the link with the engineers that we work with when building a bot, and how our work influence the results. For example, typical example, we have a lot of problems or issues with fumes in the exhausts and the exterior shapes of the roofs and of the superstructure influence these a lot, and these problems we have to solve by changing the shapes of the exhaust, the funnels, whatever. And this is really the link that we have with the engineers. It could be this could be any other problem, and for the design presentation, I would like to see how the design interfere and helps the engineers.
Okay, I'm clear.
It's for all of you, not specifically. Thank you very much.
Thank you.
Thank you, Physis, Polymi, Energy Boat. Moving on to eco-conception, can we have Neri-Id on the stage, please?
Hello, everyone. My name is Ernest Maximov, and I'm the head of the Neri-Id project, and we're going to present you our eco-conception prize of our boats for this year.
Hello, I'm Arthur, the Vice President of the project, and we are glad to participate at the competition, and we want to thank all the organizers for the competition. So move on with Ernest's presentation of our targets.
Let's start from the beginning. This is the beginning of the year in 2024, and we would like to ally reliable conception and eco-design with a performance boat. The design should be reliable, light, and of course high performance. And also we had to improve to solve last year's problems, to find solutions. We try to reduce the weight of our cockpits, to improve batteries, and also to use unsuitable materials to reduce our environmental footprint. And also the excessive use of fiber, but fiber who are directly used for fabrication, but not used for the recyclable.
So I will talk about our global approach. So this year we have chosen to totally redesign our boat because we want to introduce the eco-conception in our boat at a central point. So we start with a strong methodology. So we think about eco-design and performance optimization, because we think that there are 2 points to optimize the eco-conception: using ecological materials and optimizing the performance in order to consume less energy. So we have worked with very different industrial partners for sustainable materials. So we have chosen to use biosourced materials and to use recycled materials. So we have worked with aircraft manufacturer in order to provide us recycled materials such as fiber or aircraft panel. So we are proud to work with this type of partner. And we have also used many tools, and we have used Marine Shift 360 in order to evaluate our last year environmental impact, and we want to reduce on all points our environmental impact, and it's what we have done this year. So as I have said, we have worked on materials. So we have worked with recycled carbon fiber, Kevlar, and glass fiber. We have also worked with declaced materials, such as carbon fiber tubes or aircraft flooring for building our storage box. We have also worked on another point using biosource materials. So we have used flax fiber and biosource epoxy resin for our cockpit, because we think it's a very good solution, and it's something that is not very present in a boat right now. So we want to promote this kind of technology. And we have worked with partners in recycling and sustainable technology. So, for example, we have worked with a partner for our batteries who recycle battery cells. So,
about the weight of our cockpit and of our chassis, this is the main part of our boat where we can reduce the weight. For the cockpits, we decided to use fiber, but at the beginning of the year, we don't know what type of fiber use, cockpit, Kevlar, or we discover flax fiber, who seems to us to be a good choice. We also decided to use bio-based epoxy resin to reduce also our environmental impacts, and we achieved this objective, this aim, to reduce the cockpit weight from 45 kilograms last year to 13.7 kilograms this year. So it's a really good achievement, and we are very happy about that. About the chassis, it's a structural part, so we are not joking with this. We rebuild it from scratch. We decided to use and to create with a partner carbon tubes to do the chassis, and we also managed to reduce the weight, because last year we were using an aluminum chassis, and this year it's a carbon one. And this is, of course, lightweight, and we can reduce indirectly the energy consumption with this chassis.
So we have also worked on the optimizing of the propulsion chain. So our objective for the propulsion chain is to achieve a high efficiency and a minimum use of materials. We want to have the biggest efficiency in order to consume less energy, and it's one point that we want to move in first position in our project. So we use high technologies such as additive manufacturing, because we think by using less materials we can really improve our efficiency and our eco-conception fabrication. So we have also used recycled materials, as I have mentioned. and such as for our propulsion chain, recycled aluminium. And the advantage of this configuration is a lightweight and durable configuration to reduce our consumption and impact, because we want that everything that we have done this year is going to be very durable in time. We want to use it for many years. So we are happy of our propulsion chain.
About the battery design, this year we decided to start to research the homemade design and homemade assembly of batteries. This is in research part, this is probably for next year, but we have worked about that on the telemetry battery and also on the main battery for the motor. The impact can be drastically reduced by working with a partner who is using recycled cells. How are they doing? They are just doing that when a battery is out of usage, we can take a part of cells who can be still working for other batteries. So by using recycled cells, we can reduce drastically the environmental impacts for the batteries.
So now let's summary about our life cycle assessment results. So this year, as we can see, we have worked on every point of life cycle analysis to improve the last year boat. So we can see that in every point we have done a big advancement, and we want to continue this next year, because we think we can do better on many points. So this year we have done many key achievements. So we have obtained a very good performance. We have used lighter materials, and we have decreased a lot our boat mass. We have also worked on circular economy, because we have used many recycled and decommissioned materials. And we have also worked on durability for example, with our cockpit, because we want it to be used many years after its conception. And we have worked with low-impact, high-tech solution.
In conclusion, and for the next years, we can improve the performance, but also we can still be and coexist with sustainability and a low-impact environment. We are trying to continuously improve with mechanical pieces, but also with informatical pieces, and of course, material parts. Our objective for the next year is to be even more performant, but also to be even more less impactly on the environment. Thank you for your attention.
Thank you for another great presentation. A question from me. You mentioned that one of the big things you're aiming for is to improve efficiency, to reduce your fuel use. Do you have any stats, or do you know how much of what your efficiency gain was, and therefore what your impact reduction was just from reducing weight?
We can say that we improve our speed, our endurance for the endurance race. We don't have specs, but we are very confident, and we are very happy to prove that it's going well. And we have ideas for the next years to improve this part.
Perfect, thank you. I think from that, and as a sort of learning, I guess, is that you've got the data. I can see that you've got the really good data where you've been measuring the impact across lots of different metrics. It'd be really good for you to pick out those highlight changes to say, we've improved efficiency by this much, by reducing weight by this much, that's saved X amount of fuel, which is X amount of emissions. Like being able to actually see the specific data rather than a graph that shows lots of data that's happening at the same time would be really good for us to understand the impact, the final impact of everything that you've found out.
Okay, thank you.
Yeah, I think that's something very clear and important to share with all the team, because this year, the lightest boat is using bamboo fiber. And so you're all trying to have a very high competitive carbon fiber, whatever, but the lightest boat this year is the one that is using the most bamboo and is performing quite good. So also consider those kind of natural fibers, plus on top, consider reusing some things. You are speaking about that, but the reuse is one of the most important we all have to think in the next generation. So that's something I just want to highlight for this eco-concession prize and the future of the design. Thank you.
Thank you.
Sorry, Lizzie, you have another one.
I was going to say, does anyone else have any questions? Otherwise, I've got one. You mentioned at the end, and you probably didn't want me to ask this question, but you said you want to improve certain areas going forwards. Were there any specific hotspots or areas that had impact at the end of this year's project that you want to see, you want to try and improve for next year?
Yes, we think we could work on our cockpit, for example, by using thermoplastic resin, because we think that for now the recycling of epoxy resin is very hard. So we want to maybe next year introduce a thermoplastic resin, maybe for the cockpit or for other part of our boat. But it's an objective of next year.
Yeah, great. I think thermoplastic is going to be a really interesting one, particularly for repairs and remolding. But also, it's definitely worth looking into because it's hard to know whether those thermoplastics, when they've been broken down, can actually be used again. It's a big question about whether these recyclable resins are able to be used a second time. So I'd definitely like to see that next year.
Thank you. Thank you.
Thank you, Nereid, for sharing your sustainable approach of your team with us. Now, moving back to the Innovation Prize, I would once again like to welcome Uniboat to the stage.
Good afternoon. We are Saverio and Francesco from Uniboat. And we are very pleased to be on this stage to present to you our innovative project for marine propulsion, which is toroidal propellers. So I'll move so I don't. So this is what we designed as a toroidal propeller. And this is an idea that comes from the aeronautical sector, because it's front wing. So the idea of an aircraft without wingtips. So doing so, we applied it to propellers. And we have a propeller without any blade tips. And we know that tip vortices are one of the main causes for energy loss, for vibrations and noise. And so we think that with this design, we can have an increased efficiency and a reduction of vibration. But we also found out during our research that we can manage cavitation in a completely different way than with traditional propellers. So you see the design is a blade that closes on itself, and each, what we used to call blade, has two sections. So how to design such an object? Because usually for traditional propellers, there are softwares, there are theories that you can apply, but with this we couldn't. So what we did was we started from our requirements, so the thrust that we needed and the power that we could afford. And we ran a first design, from a scratch design, from some analytical theories. So blade element theory that we applied for most of the blade without considering the tip. So how to design the tips? We had to run an iterative design through CFD analysis. So we needed high accuracy CFDs. also both to design the tips, but also to optimize the influence that each part of the blade had on the other one. So what we did, we had to optimize the spacing between the two parts, so that, as you can see in the background, you see pressure distribution at a radial section, and you can see in a lighter color, you see the lower pressure, and darker color is the higher pressure. So what we can see is that the lower pressure doesn't really affect the lifting part of the upper profile. So doing so, we can use the optimal effect of having the two foils working together, but without disrupting the capabilities of one of the other. So we did this through simulation. So we had high accuracy runs simulation that we then validated through experimental tests. And we can clearly see here the pressure distribution of the blades. So on the left side, you see the blue parts, which are highlighted as the lowest pressure areas. And this we'll see is where we will see cavitation occur, while we see on the right side that we have different turbulent kinetic energy distribution at different distances from the hub. So in a normal wake of a classical propeller, you would have tip vortices increasing in their energy going along the wake. But here we see just below the blades, we just have the turbulence that comes from the turbulent boundary layer. But we don't have vortices anywhere in the wake except for the vortex created by the hub. So doing so, we could really see from the numerical analysis that we were already decreasing energy losses and we were increasing efficiency. Of course, after this, we needed to study the effects on vibrations and cavitation. And to do so, we went on the next step. So we prototyped our model. We produced it with additive manufacturing, and we went on with the experimental campaign.
Thank you. Yes, then we carried out with experimental text in CNR, the National Research Council in Italy, with the goal to check where the propeller's behavior matched with the result that we took in the simulation CFD. At first, we used the cavitation tunnel, in which reduce the pressure water and making more visible where and when the cavitation starts. Following, we used the towing tank, which is used to study the behavior of the propeller in a way to understand if it's the result that we took from simulation were in agree with what we studied from CFD analysis. And all of these tests help us to validate the design that we took from simulation. Following, speaking more deeply about the cavitation tunnel, we can see suddenly huge difference between the toroidal propeller and the traditional one that is in the upon picture, in which we can see that there are strong and concentrated tip vortexes that creates a cavitation zone near the blade tip. Instead, in the bottom picture, there is the toroidal propeller that has a totally different behavior. In fact, it has a diffuse toroidal, a diffuse cavitation structure. And as we can see, maybe in this part, there could be a video. Yeah, okay. As we can see from the video, but we don't have the video, so we can imagine that in the cavitation zone is not fixed, but is the cavitation zone is not fixed, but it moves with the different operating conditions, like speed or RPM. And this is a benefit just because we don't have a drop of efficiency, but we have a gradual reduction of it. And all of these tests help us to understand better that toroidal propeller is not just more efficient than the traditional one, but it also more predictable and controllable. Yeah. In this slide, instead, we can see the open water curves taken from the towing tanks, in which we can see on the right the rough experimental data like torque and thrust, and that are implemented to create the non-dimensional curves on the left, in which there are the torque and thrust coefficient and the efficiency related to the advance ratio J, in which we can appreciate that we can have a good efficiency also at, with low RPM and low speed. So, in conclusion, we can say that the toroidal propeller can have several real-world applications, like, for example, in a cargo ship, in which a longer range efficiency and also a mechanical reliability is essential, also matched with the fuel consumption. But at the same time, also in leisure yacht, in which the first request is the comfort, and so with the toroidal propeller we can reduce the noise, reducing the vibration, and so it's a good point. And another interesting operating condition is when, as I spoke before, we are with low RPM and low thrust, but high speed, and this is the operating condition of a foiling vessel. And so this is another application. And so this is our toroidal propeller concept. Thank you for your attention, and we are glad to answer all of your questions.
Good afternoon. Very good presentation and very interesting indeed. It reminds me the shower propellers which are actually on the market. I have a question about the vortices. What would be your opinion if you were forcing the vortices to create, not randomly, but in a way that you would create some small vortices, but very controlled? For example, at the head of the propeller, you have all the cavitation, which is random, as you said. But if you were creating some slight notes at the very trailing edge of the section, would it improve the performances?
I mean, if I understood correctly the question, we are energizing something like energizing the wake, is what you're talking about, or at the edge of the loop, let's say. At the edge of the loop. For example, okay. if you look at some airplane wings, at the very head, you can see some nodes at the trailing edge of the plane to force tiny vortices instead of creating a random big vortice. We didn't test such a thing, but about the tip, how to close the loop, we studied a lot of different designs, and the reason we use these in this way is because taking inspiration still from aircrafts, it works as a winglet. So its angle, it's still producing thrust in a way that it is cavitating a bit, but as we saw, not enough to create big cavitation regions. We could, of course, try to study something like how to fully take advantage of the way the vortex are kind of creating, but not really creating. Thank you. Thank you.
Thank you very much.
Do we have another question?
I think it's a very nice presentation because I appreciate very much the methodology. You showed the numerical approach, experimental approach, so I have to do you my compliments because it's a nice way of explaining an innovation. My question is just regarding what is the impact on larger ships, no? Because what we see is that you have two completely different speeds for the rotation of the propeller. Nowadays we have engines on big ships that have a very low rotational speed, and this enhances even more this aspect. Can you comment on that, please?
Yes, so about the RPM, first of all, the thing is we could design it also for a different J specifically, but the way the surfaces are merging between the two parts of the blade, it would create strange angles, so that with a pitch like this would be the best option that we found. So that's why we are sticking with the low RPMs, so that would be a plus in the application that you said. About changing the size of the vessel for which we are designing, we are working currently on that, on creating a parameterized MATLAB model to have, starting from some rough calculations, to change the spacing between the foils and the chord and the pitch distribution to apply it in a fast way to any kind of application. Of course, in our design, we're focusing on our application, so speeds around 11 knots, like the endurance speed and our thrust values.
Do we have another question? I do have two. First question, did you use this propeller today during the endurance race?
Sadly, we couldn't use it because during the testing phase, we saw that the optimization of counter-rotating for this kind of propeller is really tricky. So that's a study that we are going to do for probably the next race in Sardinia that we have in the autumn. But we focus on designing a single propeller. But in the race, it was the best option for us to mount a counter-rotating propeller setup. So at the end, we had to choose for traditional propellers.
Okay. Second question is, did you test the reaction of this propeller by going backwards?
No, actually we didn't, but we should.
Yeah. Why I'm asking this question is because you are applying to the innovation prize. So we need to be able to answer to a question about the potential market. So the potential market, as you explained, is quite huge. But we need to be sure that we can replace the propeller on an existing vessel. And most of the time, we are looking for a propeller when it's quiet. So that's, in my opinion, one of your main advantages. And the second one is you want also to be able that it's working when you do maneuver, so when it's also going backwards. And it might be a tricky point by having this toroidal propeller. So very interesting to see the result on that. I don't know if you perform it or if you have some ideas, but that might be very important. And if you can give us this example. And last is, could you please go back on the results for the proof of concept? Because I understand that you compare an existing propeller compared to your toroidal propeller, but you did not compare to a double contra-rotative propeller. Is it correct?
Yes. In the graphs, we couldn't really compare everything correctly because the values that we had for traditional propellers were just numerical, because we didn't have a chance to test our contra-rotating propellers in the towing tank, while these results were the ones coming experimentally from the towing tank. So we didn't really want to compare the two results because we validated our numerical setup for a single rotating propeller. For a counter-rotating, the numerical aspect is still a bit complicated and complex, so we didn't really want to compare with a data that could have a bias. And about the maneuverability, about going backwards, I don't have an answer, but about maneuverability, what we saw about how cavitation starts, we are thinking that we have really high capabilities for thrust at starting at very low J's, so accelerating from zero. So our opinion is that in maneuverability it should perform better than with a traditional propeller.
Okay, and last, if you develop all the software and all the calculation to perform this design, would you be okay to have it open source to all the other participants in the event in order to help them designing their own toroidal propeller?
It wouldn't be a problem, just that the MATLAB code should have a long process of becoming understandable by other people.
Yeah, but
yeah, there is no problem about it.
That's important. Thank you so much and congratulations.
Thank you all.
Moving back to the design prize, I would like to welcome back once again TU Delft Hydromotion team to the stage.
Well, hello everyone. We are the TU Delft Hydromotion team, and we are a team of 25 students, all from multidisciplinary study backgrounds. And we all have one shared mission, which is to drive the maritime industry toward a cleaner and a more sustainable future. But we also have another mission, which is to educate the engineers of the future. That is similarly important to us, making sure that the generation of the future that will build our future boats actually is engaged with the environment and trying to make a better world. And by taking on the mission of demonstrating the power of liquid hydrogen, we have aimed high and have taken a lot of difficult challenges, and we also had to take a lot of risks. But those risks for us were worth taking, because for us, playing safe is not going to change the environment. And now our mission is to demonstrate the power and the potential of liquid hydrogen on an international level. So what better to do it here in Monaco? And as a TU Delft Hydromotion team, we aim to push the boundaries of a sustainable innovation by showcasing that how hydrogen can drive the future of maritime technology. Through cutting-edge engineering and global collaboration, we strive to prove that liquid hydrogen is not just a possibility. It is a powerful solution and ready for the challenges of tomorrow, and it's ready to fuel the future. And while we use liquid hydrogen, we also use a foiling system. While foiling, we try to minimize the contact between the hull and the water, causing the resistance to drop, and to also drop energy use, which is going to be more efficient. And this advantage is really essential for us, especially on longer distances. And Mira actually uses, Mira is our boat, and she actually uses an active foil system. So that means that while foiling, we constantly keep adjusting the angles of our foils to make sure that she is at the perfect height for us. And in the front of Mira, we actually have a sensor which is measuring the height at which we are foiling. And at the same time, this also tracks her acceleration. And the sensors are also, enable us to control the stability of our boat. And for us, our pilots are also really important that are in our boat. And Mira is equipped with an electrical steering wheel, as you can see here, which is reducing the physical strain of the pilots, and this also allows us for smoother control, which can be really nice for long distances and for tight maneuvers. The boat is also featured with comfortable seating and with quick-release seat belts, And they are both for safety, but also for ease of use. And besides the comfortable seating, Mira is also equipped with a control box and a screen, as you can see here, so we can control all of our systems live.
Yeah, so thank you, Maureen. So this year we've also introduced liquid hydrogen, as has been said a few times today. And as you can see in the picture below, we've have quite some space left, but that's because at the beginning of the year we did not know how big our liquid hydrogen tank would be. We knew that it would save space, but we didn't know exactly how much. So that's why there's quite some space left. The shape of our liquid hydrogen tank is actually a bit different compared to the shape of a compressed hydrogen tank. As you can see, it's a lot smaller in length, but while it's smaller in length, it has a bit of a bigger diameter. This is to improve the ratio between the volume and the surface area. This is because you get less of a boil-off when the surface area compared to your volume is lower. After that, our hydrogen passes through a fuel cell and we generate electricity. So, to continue. We have chosen to build a liquid hydrogen-powered boat to show the maritime industry that the possibility of sailing on a sustainable energy source is already possible. And we know that it might be difficult for companies to take the next step and take the leap towards this, because probably costs will be higher. But we believe that we can gain traction with the media and people in the sector by doing projects like this, showcasing what can be done with green energy. Making a foiling hydrogen-powered racing boat is quite interesting for people to see. And it can take people into the story of sustainable energy and of sustainable hydrogen.
Yes, and now we have talked a lot about what's going on inside our boat and also below our boat, but the hull of our boat is also pretty special. The slender and streamlined shape of our hull is both beautiful, but it's also really practical. With a bow that is sharp enough to cut through the Monaco waves and a chine that steers the water around the hull and away from the deck, and a length that is suitable not only for speed, but also for maneuverability. Mira is by all means designed to perform. And however, performance is not everything to us. For us, sometimes we have to compromise on efficiency in order to be sustainable. And that's why we try to implement Flex this year, which is the first time in hydromotion history. We actually used Flex, which is biocomposite, and Flex is 30 times more sustainable than carbon. It has a 30 times lower carbon footprint. And we actually accomplished to use it for 15% of our whole boat. So, for example, we used it in the tank hatches, in the dashboard, and in some of the internal structures of our boat.
Yeah, so as mentioned before, our boat sails on hydrogen. For those who don't know, hydrogen passes through a fuel cell. And the beautiful thing about hydrogen in combination with a fuel cell is that the only thing you emit really is water vapor, which is obviously not that harmful to the environment. To produce hydrogen in a green way, you actually need electricity first. You need to perform electrolysis and split the water into hydrogen and oxygen. By doing this, you might think, well, why would you not just use electricity immediately? But that's because storing hydrogen as an energy source on a boat is way more compact than just building a big battery in your boat. If we would build a battery that contains as much energy as our hydrogen tanks, we would need to build a bigger boat, and our boat would be a lot heavier. Thank you so much for listening. I hope you've now gotten a better insight into the design of our boat. And if you have any questions, we look forward to answering them.
Thank you for your presentation. Any question? No. Belly, yes, we have. Oh, Baba. How? Oh.
Hello, thanks again for your nice presentation. I have one question, is regarding the tank, hydrogen tank. Is cylinder the best shape to minimize the ratio between surface and volume?
No, that's a very good question or remark. It would be better to have a spherical tank. That is probably quite obvious to maybe everyone in the room. But when we started our project this year, we did not know at first even if we were going to do liquid hydrogen, methanol, ammonia, we did not really know. So we had already had to make the design constraints and the design of the hull of our boat. So, and then to fit in the liquid hydrogen tank, it had to take on the shape of a bit of a flatter cylinder. So very good question.
Thank you.
Yeah, we actually also reused the mold of our 2023 boat because implementing a liquid hydrogen tank takes a lot of time from all of their team members, and we only had 1 year. And that's also why we decided to reuse the mold, since in 2023 it performed really well here at the Monaco Energy Boat Challenge.
I do have one question maybe for the other team and member in the room. That's a very important question for liquid hydrogen, the shape of the tank, but maybe also you discover something that the other people that might have an idea to use the liquid hydrogen do not, is the G-force and the impact on what's happening inside the liquid hydrogen. Does it increasing the boil-off? Do you have an issue by the G effect on the liquid hydrogen directly inside the tank? And what was the feedback due to the impact on this hydrogen, let's say, tank?
Yeah, so it is quite a difficulty for liquid hydrogen tanks and G-force. But at the start of the year, we looked at some data of the previous years of our boats and the maximum G-forces it really took. And then we took a safety factor, so it can withstand forces higher than 4 Gs. But I'm not completely sure, so I could be wrong, but if you want to be able to make your tank withstand more G-forces, then the inner tank should be better connected to your outside tank, which would increase the surface area of the connection between the outside world, basically, so your boil-off rate would increase. So for a foiling boat, it might not... Well, for a foiling boat, you need more G-forces probably because you have the chance of landing and going quite fast. But if you do not implement it in a foiling boat, then you probably need to be able to withstand less G-forces.
Yes, I have a question. You talked about a lot about all the technical aspects of the boat. What my interest is what we can see from the boats, what drives you into the exterior design or styling of the boat, and what's the origin, what was the idea, and how do we end it with your design? The visible part, so above waterline.
Yeah, so do you mean like the shape of the hull or like the wrap around it, or?
The styling, so everything that we can see above waterline, so not the hull shape,
yeah,
everything above.
Yeah, to begin with, I don't know how we can go back to one of the pictures, but on top of our tank caps, you can see a swoosh of brown. It's actually not just brown, it's you can actually see the flex fibers. Yeah, you can actually see the flex fibers through the design. And the side of our design is we wanted to create a world that is already really busy with being sustainable. So that's why we chose the blue water and the fishes in it. And the fishes you can see in the back are actually the spirit animals that were from the last few years. because all the people that were in those teams also really helped us create our boat. And then you can see the lionfish in the front, which is our spirit animal.
Thank you.
Thank you.
Thank you, TU Delft. I believe you took TU Delft. I think you took my program with your papers. Thank you. Thank you for presenting the design of your innovation. Now I would like Elettra to come back for the Eco-Conception Prize.
Good afternoon. My name is Sara Baravaschi, and this is my colleague Pietro Cipollini. We are representing Team Elettra from the University of Genova. So today we're going to talk about the Eco-Conception Prize and what we as a team try to do throughout the year to impact as less as possible talking about the environment. So LCA, a life cycle assessment, was requested for the Eco-Conception Prize. It's an exceptional tool to actually quantify the impact, to give out numbers. We're engineers, we like numbers over words. We used, as the other teams, the MarineShift 360. That is a very great tool to give out numbers. And another thing, it is used by professionals, so it also gave us an insight about how professionals actually work in real jobs. So, timeline. How was our project organized? We tried to think about the past, to learn from our mistakes, from the logistical and technical mistakes. We tried, talking about the present, we tried to buy components that were that had a rate waste very low. Our rate waste was around 6.59%, which means that we used very efficiently our components. So this is about the present, and about the future. We try to have a forward-thinking mindset. We try to develop a boat that had a structure, that had flexibility, modularity, so we could actually reuse it also for the next projects, for our next vessels. So now I'm gonna talk about certain aspects that aren't easily to quantify, the data at the very last of the presentation, such as the hulls. The hulls presented some damage from the past year, so we decided to use some patches made of fiberglass to prevent the hulls to take on water. Talking about maintenance, that is a key point to be as less impactful as possible. The cockpit, that is made of flex fiber, we used it also in the past year, and an advice to the other teams, it's a very great fiber, but it has some disadvantages. For example, the moisture, it tends to absorb more moisture, and UV degradation has a big impact. We needed maintenance, so we repainted it, extending its life. Talking about materials, this year we used PLA, which is very good. It has a very low impact compared to the other type of filaments for 3D printing. Many components of our boat are made of PLA, the propeller, the basement of the TLC, the connections to the traverse, and the throttle itself is made of PLA. It has great mechanical and thermal resistant properties. And great thanks to our naval team that redesigned all the components and 3D printed them. Okay. So the weakest point is our propulsion system, so the inverter and the motor. We totally changed it from the past year. It's a competition, we try to be competitive, so we had to buy a new motor and new inverter. And what did we took into account this year? We tried to take into account take in account to buy something with higher quality, so we could use it for other competitions. And we aimed also to higher efficiency and higher performance. Okay, another key point, as I already said, the modular design of our structure. This year we used 2 aluminum bars with a circular section, and the components are attached to the aluminum bars with collars, so we could move around the various components, aiming for better trim, better redistribution of weights, so better performance, better efficiencies. Another aspect is the short supply chain. We are from Genova. Genova is a sea city. It has a very advanced economy, a maritime economy, so we could collaborate with local companies, decreasing the transportation impact, and also supporting local companies, which is also very important, not strictly related to the eco-conception prize, but it's still very important. Now I give the word to my colleague.
Thank you. So we talk about LCA. Now let's talk about the LCA results. So for what matters about CO2 emission, equivalent CO2 emission, as we can see in the production and use and end-of-life calculation, the bigger impacts are coming from hull and structures and propulsions. This is due to the carbon fiber of the hulls and considering all the propulsion, as said before, and this impact is the most respect of the other materials. For what matters about mineral resource scarcity, as you can see, the 75% of our impact comes from propulsion, because we have aluminium, which is a very have a big impact as a number of in weight. We have also the batteries, which is made from lithium, nickel, cobalt, and manganese, and also from the copper inside the cable inside the batteries, which takes a few kilos. Then, talking about the energy consumption, as you can see the results, the hull and the structure were the 55% circa the bigger contributes. So we can go on. Then for what matter about the energy consumption renewable, at the same time the propulsion and the hull and the structures were the biggest numbers in this area. Then we know that batteries have a lot of impact in the propulsion and the emission sides. So last year we built our first custom battery, and this year we had to choose to buy a new battery because we have different constraints, technical constraints, or to disassemble our old battery and do a little bit of maintenance, rebuild it, and this approach allows us to reuse the cells, but doing that we also discovered some facts about that some cells were damaged, so we could repair it physically, like mechanically, or maybe we had to add 2 cells, so we had to fit these new cells that are not degraded into the backwards, the last year cells. And so this allows us to reduce the CO2 emissions and also the index in mineral resource scarcity. So this approach allows us to reuse the cells. And not only for this competition, we are planning to, again, do this approach to allow us to reuse the cell also for other competition in order to not buy every time new components that will be used maybe in 12 hours by a year completely in like a cycle. Thank you for your time. and we are ready to answer some questions.
Perfect. Thank you for a great presentation. One question, I might need to just skip back a little bit, but you present the carbon footprint of the initial, so back a few slides, it shows it against the production, use, and end-of-life phases, this one. Out of interest, why is your hull and structures use phase? Your use phase is really high. I'd be really interested to know what have you included in that use phase that's making those numbers that high. Propulsion makes sense, but the others I'd be really interested to know.
Our hulls that we use for our sea trials are made of carbon fibers, so this is the reason behind this high percentage.
But my question is...
sorry, I didn't.
No, that's, yeah, I understand, but between the split, so I'd understand why in production, high use of carbon fiber in the production phase would mean that you've got...
I think it's the production phase is also included the repairs, so
Okay.
maybe this is the reason why it's so high.
Okay, so in the use phase, it's referring to like maintenance and repairs and stuff that are doing it. Okay, great. No, that's good to know. Just looking at it, interesting. But yeah, if it's for maintenance and repairs, then it makes sense that that's in the use phase. Does anyone else have any questions? Because otherwise I have another one. My other question is, you mentioned early on about modularity. What have you introduced? Can you give an example of where you've got modular features and how you're going to utilize those features later?
So the structure is made of 2 aluminum bars, and as I already said, it has a circular section. In the past year, we used also aluminum bars, but with a squared section, and in order to fix the component, we had to drill a hole and fix the component. Whereas this year, we use collars, so we can move it easily around. And if we have to upgrade our structure, we can simply put away the box and reuse the same aluminum bars. So that's about the modularity, and it has also an impact on the efficiency, because I'm not a naval engineer, but the center of mass of the boat has a very big impact on efficiency and on the resistance while moving.
If I can add another things, this allows also for us to have a durable structure, because we do not have to drill inside the beams, and so we don't destroy by little bit by variation of position the components. Furthermore, we can add different components. For example, if we want to change maybe the capacity of the battery, or maybe add some PV, something like that, we can just have a standard collar, which can and a standard width that we can design and just place it. Thank you for the question.
No, that's a great answer. Thank you. Any other questions? Yeah. Thank you, guys. No more questions for you guys.
Now moving on to the last finalists of the Innovation Prize, can we please welcome Heriot-Watt University to the stage?
Okay. Hi, everyone. Thanks for sticking around. I know it's been a long day. My name is Kate Sinclair. I work on the technical and creative aspects of the boat.
And hello, I'm Dominic, and I'm the team lead for H2R, and this is our first ever entry into the Monaco Energy Boat Challenge, so thank you for having us. And today, I'm going to be talking about implementing metal hydrides for safe, steady-state hydrogen storage. Okay, so why should we even care about hydrogen within the maritime industry? Well, currently, within the maritime industry, it accounts for 3% of global emissions. And this means we need to decarbonize fast. Most countries have an aim to decarbonize by 90% by 2050. And the maritime industry at the moment is only decarbonized by 2%. So we need to do at least 30% every decade from now. And that's a lot. We need to move fast. So one solution is hydrogen. Currently, there's an incredible ramp-up of hydrogen production within Europe, and it also allows for benefits you wouldn't get from using just batteries. For example, you'd be able to refuel remotely. You wouldn't need an electrical connection in order to charge a battery or refuel your boat.
Okay, so hydrogen, how is this feasible? So we've seen this working in real life with one of our sponsors, Forth Ports, at their green hydrogen shore trial, which was about a month ago. So at Forth Ports, which is at the port of Leith, they have a fully hydrogen running trawler. Yeah, they have a fully hydrogen trawler, sorry. So that is working by having a solar panel set up on shore, which is then transferred into a greener hydrogen running boat. So, you know, this is working in real life. It's reducing idling boat times and curtailing to renewable energy. So it's really impressive and it really works and it's happening. Slowly and surely. So I think I'm really sorry to the other team. We're going to have some conflicting hydrogen information, but we'll see how this goes. So looking at the options for storing hydrogen, we have pressurized hydrogen, cryogenic hydrogen, metal hydrides, and complex hydrides. So looking at cryogenic hydrogen, we moved away from this as it has to be stored at absolute zero, and we find this is quite complex in real life. It revolves around a lot of kit, and it's just not very realistic for us. We then looked at complex hydrides, but as in the name, they are complex. And they involve a lot of chemical reactions that we don't really know anything about. So that involves some safety problems and things that we can't really control, so we wouldn't go for that. Looking at pressurized hydrogen, obviously this is happening and it's working, but it still has to be stored at 700 bar, which is obviously very high and can have its own problems. Therefore, we decide to look at metal hydrides and see how that would work, because we think that would be a great solution for this problem.
Okay, so I bet all of you are wondering right now, like, what is a metal hydride? How does that actually work? Well, here we go. So we use a magnesium titanium hydride. And as you can see here in this lovely animation, the metallic layers of the metal are set, and when exposed to hydrogen, it absorbs the hydrogen atoms within the layer. This means that there's no actual gas within the system. It is purely a solid state piece of material which happens to include hydrogen, and this can be deabsorbed on command as well. This technology can be recycled for 3,000 times or more, so you can repeatedly use it a lot. It's only stored at 1 bar and 20 degrees, so the issues you had with compressed hydrogen and cryogenic hydrogen with the amount of safety systems you need to maintain that pressure and temperature, you don't really need to worry about it with hydrides. Also very high hydrogen purity and a high volumetric density, which we all know is very useful for the maritime industry. And I touched on this a little bit. This comes with really good safety applications. You could cut a hole into a metal hydride canister, and maybe a gram of hydrogen would be released before the material oxidizes and self-seals itself from the environment. This is completely a different story if you were to do that to a compressed hydrogen tank. This would exert so much hydrogen you'd have a jet fire and potentially your boat would be in flames. So it's a much safer solution that we can apply within our boat. And so...
Okay, so we've seen how they work, so how do we use it for our boat? So we have our metal hydrides, which then connects to a fuel cell, which then connects to a battery, which connects to our electric outboard. So we use a battery so we have a constant steady state of power coming out of our boat, just to make it more reliable, and the hydrides can also be used as a range extender in this way, and this can improve shipping distances and just all over help decarbonize and move towards net zero. So this is an example of our boat. So this is us at the Forth Ports Open Day with the experiment of Leith. We use a recycled 30-year-old hull, and as behind you can see the trawler, which is the fully hydrogen-powered equipment that they have at the port, close to home for us in Edinburgh.
So it's not just us using this technology, this has been used for a long time. For example, there was a German Type 12A submarine produced about 30 years ago, which integrated hydrogen or metal hydrides. And this helped because they're heavy, you can go down as fast as you want, and you won't need to use the weights that you usually would. But also in newer naval vessels, such as the Zeus craft here, and this is the size you would use for a short-term ferry. And so this technology, although not abundantly used, not chosen commonly over compressed or cryogenic hydrogen, it is being produced and it is seen to be feasible. But that does raise the question, why aren't metal hydrides used en masse? Well, they have complex manufacturing. I mentioned before, it oxidizes when in contact with the air, with oxygen. And so to manufacture this product, you need to have an inert manufacturing facility. You can't have any oxygen getting to the raw material. It is quite heavy, again, not yet mass-produced, and the safety standards that are currently in place for hydrogen are set towards cryogenic and pressurized hydrogen. There is not an instruction manual which tells you how to integrate a metal hydride system. So, how do we make this feasible? Well, there's worldwide production already. There's factories in Japan, Germany, the US, France, China, Australia, all over the world. And so there's competition there which will spark a push forward for larger manufacturing facilities. You'll reduce your safety costs. In this economy right now, everyone wants to be reducing costs, and if you're to build a boat that uses hydrogen and you need to put a massive hydrogen safety system in there and reinforce all your bulkheads, that's going to cost a lot of money. So maybe using a more cost-effective solution from the safety point of view might make this product more applicable. And I'll touch on this again, there needs to be a specific metal hydride standard in order to create that instruction manual of how to implement this safely and so that people understand how this technology works properly. And so, how do we apply this to the market? Well, hydrogen in particular is great for short-term ferries. You can have 2 ports which will refuel your boat with hydrogen. It's a repeatable distance, and you can keep going back and forth between those 2 ports again and again. And this can be used around Europe, as you can see here. Using boats like the Zeus ship, we could use metal hydrides within industry, within ferries, to move people around, transport goods, and decarbonize the maritime industry for good. So, thank you very much. We'll take any questions that you guys have now.
Thank you. I'm sure we're going to have plenty of questions. Please go ahead.
Thank you very much for the presentation. I have one question. Did you make the evaluation on how much is the energy density and how much this could be the impact on the navigation on the boat, on how much is more the consumption, on the range that you can get, and how the layout of the boat could change in order to host this amount of energy or this different storage method?
Yeah, absolutely. So I've got a table here of all the volumetric and gravimetric densities that we need. So metal hydrides have a better volumetric density than compressed hydrogen, and so you can put more cargo in your boat. It's better than batteries, compressed hydrogen. It's in terms of hydrogen production or hydrogen storage, it's the best volumetric solution.
I'm sorry,
yeah.
Can you give?
You want it closer?
No. Can you just give the number?
Oh, cool. 2.5 kilowatt hours per meter cubed. No, per liter.
Yeah. Do we have another question? Yes.
Do you think that metal hydrides are uniquely suited for autonomous boats because the lack of safety systems and the fact that they don't necessarily need that same oversight in stuff like autonomous fueling or other operations?
I think that's a really good question. Yeah, you don't need to be constantly monitoring the state that compartment is in. There's actually one place where metal hydrides have been used before in an autonomous system, which is with drones in Ukraine. They use metal hydrides to power their drones and fly around with that, and that has no onboard monitoring. So that's a good application for this, and maybe a team could pick this up in the next year of the AI class.
Thank you. Could you please share a bit, because I know you tried to do a sort of a good presentation, but there is also many limits that was not highlighted in your presentation. Could you give us an idea about the maximum pressure output you can have from the tank, and also the maximum, let's say, quantity of hydrogen per hour we can have from the tank, please?
Okay, so sorry, the two things you want, so maximum amount out the tank, and the other one?
The pressure and the quantity.
The pressure, so the maximum output pressure is about 7 bar out of the tank, and the quantity of the output, I don't have the exact number for you, I'm sorry. I could ask I have someone who's worked in hydrogen for a long time in the crowd.
Sure, you can ask.
Yeah. Do you know? Kilowatt hour? Yeah, kilowatt hour. Okay, well there you go. Better than compressed, about the same with liquid. I'm sorry I can't give you numbers at the moment, but there you go.
Okay, and last, could you please give us some example? Because if you go back on your synectic, unfortunately, I know that you were not validated by safety reason, because you have no separation in between hydrogen and the battery. It does not, no, previous, it does not change the quality of the thing, but could you give us an idea about the power of the fuel cell, just for everyone have an idea, clear idea, because you know, it's a synectic like look goods, but it's important to give numbers on that.
Absolutely. So within our boat, we use the metal hydrides as range extenders. They weren't they were extending the battery capacity. The output of the fuel cell was 1.25 kilowatts, which is enough to charge the battery in downtimes of the motor. So there you go.
Thank you. Do we have another question from jury?
You said the volumetric energy density was better than other technology, but what about the energy density in kilogram?
Yeah, absolutely. So also on my handy iPad. So which one am I looking at here? That one. It's 1.5 kilowatt hours per kilogram.
But is it better than other technology?
So it's better than compressed hydrogen, or about the same as compressed hydrogen. It is worse than liquid hydrogen, but this doesn't include all the other safety applications you need to include to make liquid hydrogen a sustainable process. So, yeah.
Just to be sure, you say 1.5 kilowatt per kilo? 1.5 kilowatt hours per kilo?
1.5 kilowatt hours per kilogram.
So it's 10 times less than diesel?
Yeah, but so is compressed hydrogen.
But you are not considering, yes, you are considering the full tank compared to this just amount of 1 kilo of hydrogen. So you need to compare apple and apple, gentlemen. Huh?
So
if you are considering 1 kilo of hydrogen on 1 kilo of your tank, you need to compare everything the same. Huh?
Yes.
Okay. Okay, one last question. Because you are the first applying that to the Monaco Energy Boat Challenge, and congratulations for that. Could you share the tricky point you face, the issue, the price? Is it expensive, not expensive, easy to use, not easy to use? Would you recommend to the other team to try to use that, or you just say you have to use that because they pay you to say that? You know, it's important just to share in reality in all this family of the Monaco Energy Boat Challenge.
No, absolutely, and good question as well. So if we go back to we'll just put our boat on the screen here for now. So yeah, this is our first, thank you as well for the introduction. This is our first entry into the Monaco Energy Boat Challenge and using metal hydrides. And we did face a lot of challenges in terms of getting this boat here. We only started this entire project in January. And so we didn't have a lot of time to put together a full system. We didn't pass the technical inspection because we didn't have a compartment between the hydrogen and the battery facility. And I think I touched on this just needs to be validated, but with safety standards which are adhered directly to metal hydrides, I think the fuel has a lot of potential to not have to have the same regulations that compressed or cryogenic do. And so that may reduce the complexity of a system that we have to build, although we're always happy to adhere to technical regulations if they're required.
Yeah, sorry. I was just saying, and we also had problems just due to the sheer size of the boat. It's a very small boat, so it's a very small space to fit the fuel cell, batteries, hydrides. So that was a big problem for us, but we were trying to go with a sustainable front with our hull that we were reusing. Obviously, we'll try and bring a bigger boat next time and keep everything separate. But yeah, I think it's a great possibility and it's a great thing to use, and teams shouldn't be scared of it. But with the safety regulations, obviously it does make it difficult, but with so many places in the world trying to push forward this technology, hopefully things will be moving very quickly and we'll be able to have this kind of used worldwide.
And just to add on that, you said, would we recommend it to other teams? I would say when the safety standard comes in and we have a rule book which says this is what you do, yes, do it then. But
that's the case, huh?
Yeah.
That is the case today. In the energy class, they have a proper documentation about what they have to follow.
Yeah, exactly. There's no instruction manual, so.
Okay. Thank you so much. Congratulations, and looking forward to see you next year.
Thank you, Heriot-Watt, for sharing this innovation with us. Now, I would like to warmly welcome back Uniboat, but this time for the design prize.
Thank you. Okay. Good evening to everyone. I am Alessio, she's Tecla. We are from Uniboat, and today we are going to present the complete redesign of the cockpit of Futura, Uniboat's energy class prototype. So, we started from a question. Why redesign our cockpit? Well, the first reason was because it was worn out and outdated. It was also inefficient in the use of the inboard space, giving too much legroom for the pilot and too much less space for the torso of the pilot, eliminating so the possibility to stay comfortably in the boat, and also by forcing us to mounting the instrumentation on an auxiliary bracket outside of the cockpit. And then it was improvable from the aerodynamic point of view, and also it lacked of an aesthetic appeal for a boat. So we based our design process for the first time by a complete redesign, starting from scratch for a cockpit for Uniboat. And we based this on an industry type of design process, starting from a technical point of view, by overcoming and also studying what was technical requirements, and also by designing some proposals on top of that, in order to take the complete advantage on which was the constraints deriving from the technical requirements. And then, with the implementation phase, when we studied how to engineer at the best as we can, and also our partners can, the entire boat. So, starting from the requirements, we had 6 requirements, which was accommodate pilot, with a height of circa 1.7 meters. And also, the second requirement was to have a cockpit that was easy to service, and also improving the aerodynamics of the boat in order to gain so much more speed. And then it needed to have some safety and regulatory compliance, and also it needed to be lightweight because it is a race boat. And then we needed to research for the appliance of eco-friendly materials. So we started from shape. The shape were taken from our fellow students' project, like Uniboat Motorsport, and also on the Sorare with Emilia One solar bicycle. And then I take the mic to Tekla.
Thank you. So one of the most critical components that we had to focus on was the air intake for the fuel cell. So we explored different options, looking at past year solutions, but we also looked for new solutions in the automotive world. Our attention was caught particularly by the NACA duct. But the problem was that each of these solutions alone didn't meet our requirements and had different drawbacks. So finally, we came toward this hybrid solution that combines NACA and scoop inlets that gives us the perfect balance between aerodynamics performance and the airflow that we need for the cooling and the fuel cell inlet. Then the outlet was just the natural continuing of the cockpit shape. We took automotive-inspired shape, but we also draw influence from early naval design, such as the transom of the 19th century transatlantic. So we tried to blend performance and heritage in a coherent visual image. Then this design also introduced modularity. So our cockpit now can adapt to different powertrain configuration. And we have the hydrogen battery hybrid configuration or battery only.
So, talking of sustainability and recycling, we decided to recycle the old structural component inside the cockpit. This was a key choice in order to reduce the weight by cutting some pipes, and also it had an eco-friendly approach because we didn't need to basically make a new component. And this was also in a part capable of gaining more space on board of the boat. And the ergonomics were studied taking as reference what's the motorsport. So the sports car ergonomics, motorcycles ergonomics, shaping the entire fairings of the boat around the pilot. And in order to do this, we decided to study everything around the 35% man and an 80% woman. And this set us those two measures, chair height and back angle. The chair height was 140 millimeters, and the back angle was of 28 millimeters, which was the perfect compromise for a good aerodynamic and also a good comfort and also, lastly, nice visibility.
Sustainability was one of our goals, and it played a central role in the choice of materials. So, as said before by my colleagues, we were able to build the entire cockpit with linen fiber and thermoplastic resin that, as we know, makes it better recyclable compared to carbon fiber and thermosetting resin. But we didn't just try to choose the most sustainable material. We, as I said, for the structural component, we tried to give a second life to the already existent components. So we reused the steering wheel from 2023 edition. And then, as explained, we made the seat entirely by expired carbon fiber that we then covered with orange peel leather.
And so, by definition, design is the perfect blend between form and function. And delivery is one key point of this. It's a good example because we choose to implement on the boat one of the main symbols of Bologna, the trident, and by implementing inside the trident the reflective material, we managed to be safety compliant to the reglement, and also we decided to enhance the safety of the boat by including some satin wrap finish in order to minimize glare, and so giving to the pilot a better comfort of view and also minimizing the glare. So the cockpit windshield was a key feature by this inspiration from motorcycle fairings, by giving protection from windshield, from the wind, and also we were inspired by a hand dryer, a very popular hand dryer, made with a particular carter in order to reduce the glare, the glaze for the users, and also by adopting a matte black finish in order to minimize the glare. This was a reference from the aircraft world, like here we can see the Canadair with this black cockpit. And then for finish, this is the result. And it was mainly the choral work of an entire team for every single department by implementing something that was with an eye on the performance and also an eye on the aesthetic, because this is a boat that can do 30 knots, and so it needed some performance study. And this is it. Thank you for your attention.
Thank you very much. Any question?
Good afternoon. Thank you very much for your presentation. I have that's a perfect example of the design in the form and functions. Could you elaborate the challenges you had in production to put in shape such forms?
Surely. Mainly, one of the key problems was how do we manage to give a shape in order to reduce the waste of materials, but also in order to reduce what is the weight of the cockpit, by also giving to the cockpit this eco-friendly material, which is linen fiber. And this was, for example, a key feature because if you see our cockpit, it has not such really creased lines. Everything has a perfect rounding because that radius had the capability of reducing the quantity of resin, and so by reducing resin, we managed to keep the weight lower, but also to keep the same strength. This was a key feature, but this is one. And another was the implementation of aerodynamics. We tried and tried and tried again to redesign everything in order to minimize as much as possible the CX for the entire cockpit of the boat, and also the implementation of hydrogen, because making something that has two architecture for the powertrain is not so easy. It's like making a car electric and also by combustion engine. It's not something that it's like, okay, plug and play. But we managed in some ways to put everything all together. And this was a really complex challenge for the entire team, I think.
Thank you very much.
Thank you. It's not necessarily a question, but the presentation was very good and encompassing all the elements that we want to see in you competing for the design prize. I also like the idea that livery, the paint or the graphical elements on the boat are not only there for the aesthetic, but also as a meaning and function. That's pretty good. And as well, question that I also asked to other team, can you evaluate the amount of improvement that you had, because you were talking about air drag, CX, and how much you have gained, improved this?
Surely. Mainly in CX, we are talking about 9% decrease, sorry, in 9% in performance. So it's less 9%. And that was a key feature, because our main goal was to make something that goes fast. And making something that goes, for example, as we've seen, like 27, 30 knots, it's not only in one direction. It means that when you have the wind outside of you, you need to not only be pushed, but also to not be pushed. For example, when you have side wind, we tried as much as possible as to decrease the section, and that was the main part. We cut almost the 15 to 20% of the entire side of the boat, if you see it from an orthogonal view. That was a really helpful decision in order to increase not only the performance in the straight line, but also the performance between the slalom and maneuverability in not ideal conditions. That was really a challenge, really challenging. So thank you for the question.
And let's continue on that. Could you share with us, sorry, I am a bit the technical guy, the difference of drag you have in between the water and the air? Do you have this percentage of drag you are having in between the air and the water?
I'm sorry, in which sense? In the air?
I don't know, let's say, you know, the America's boats, they have 50% of drag inside the water and 50% of drag in the air. Normal motorboat is having 85% of the drag inside the water and 15% in the air. Do you have an idea about this compromise in between on your boat?
Mainly, okay.
I think in our kind of boat, the main drag is in the water. So I can't give you a percentage of it, but yeah, like the air drag, it's lower than the water one. But yeah, it all contributes to the performance of the boat. So we just try to better the one that we have power on, since you give us the hulls.
Thank you. And maybe one last question. Do you have an idea about the next evolution you're going to do next year?
Since we hope to implement hydrogen, we didn't compete with hydrogen this year. We for sure redesigned the battery box and then the like the chassis for the cylinder. I think we did enough work on the cockpit, so yeah, for that we are done, let's say, and we'll move to the other part of the boat.
And also, one key feature can be the entire controls of the boat. For example, the UX and the UI of the software that makes everything work, but also the accelerator of the boat. Because we are electric, and that means that you can overcome something that in a classic engine is made with just cables and leverages. We can do a potentiometer and also construct everything around a simple architecture. That is a key turning point for the design standing point. Sorry for the repetitions. And also the entire side of, let's say, how we can make better what we haven't changed this year. So, for example, the entire structure of the support for the steering wheel and instrumentation, trying maybe to gain more sustainability points by adopting some new materials, like has we seen vegetal-based composites or things like that. We will check it out in the next future to see if it's something that can be really really powerful in terms of development of the boat.
Thank you so much. Gilles?
Okay. Thank you very much.
Thank you.
Now, finally, but not least, let's welcome the Redwave team for the Eco Conception Prize.
Thank you. Thank you very much. Hello everyone, have a good evening. I'm Majid and I'll be presenting LCA comparison of the electric and fuel propulsion system for Foki 510 sailing. Okay, oh, it's went. Okay, at the middle. Okay, here we have a quick agenda about what we are going through, from study objectives, component breakdown, and to the key results, and open question and future insights. Our goal was to implement a comparison, LCA comparison, between the fuel and electric propulsion systems. And this comparison is provided by MarineShift 360, and our focus was on the use phase. Use phase providing a perspective based on the users and customers and investors' point of view, whichever system you use, the emissions will be attached to that choice. So we implemented this LCA, and our scope is 2,000 hours of the operation during the 10 years, which is a median amount of operation for this kind of boat. Well, let's go to the system breakdowns. For each propulsion system, we considered the major components, like in this case, the electric one. We considered the frame, plus the drive, which is electric motor, and battery box. The category of the components are based on the MarineShift categorization, including 4 main categories, with the main material and the total weight. For the electric propulsion system, we can see that most of the weight is dedicated to the battery box. And at the total, it rounds up about 185 kilograms. We consider the same approach for the fuel engine as well, considering the frame with the mechanical component inside, and the drive system, which is internal combustion engine and the starter battery. And in this case, which this model is one of the sophisticated ones in its own self, the drive weight is 104 kilograms, but we also considered the weight of the starter battery and the fuel inside of the tank as a total propulsion system. So it ends up at 135 kilograms, which appears a bit lighter than the electric one. So let's dive into the results. As CO2 emission is peaking, we can see that electric motor emits 40% less CO2, standing at a number of almost 34 tons of emission, while the fuel motor has the 55 tons, creating a disparity of 22 tons of emission. So if I want to give you an idea how much is 22 tons of emission, I invite you to look at this picture. This huge balloon you see representing only 1 ton of CO2. And the size and the scale is pretty good, comprehensible by the people standing at the side. So now imagine having 21 more of these balloons stacked together for that amount of emission, which in the mass production, this is for the one unit, only one, and in the terms of mass production, it would be much more. Let's talk about mineral resource scarcity. So, electric motor uses 7 times more rare material, and that's because of the batteries and the components inside the battery box. We all know that already today we are using lithium batteries, which they contain cobalt and nickel, and also a considerable amount of copper for the electric component. This makes a disparity in comparison with the electric motor and fuel motor. In terms of energy consumption, we can see also electric propulsion systems standing in a higher point comparing to the fuel motor, using 6.7 times more energy in terms of production. And I think one of the important ones is about marine eutrophication. If I want to give you a brief explanation about this phenomenon, is the water pollution when nutrients entering the water causing algae to grow, and as they grow, they cover the surface of the water, prohibiting sunlight to reach inside the water. And also, this kind of algae, they consume a lot amount of oxygen, which can be a potential threat to marine life. In comparison, the electric motor also causes 3 times more marine eutrophication. So, let's have a break. I use this funny picture to send a profound message. So, what we're doing, are we doing a good thing, shifting from electric to, fuel propulsion system to electric ones? Well, I may be standing at the right side, thinking about all the positive things, being optimistic about electrification, but also I may be standing at the left side and thinking about all drawbacks and the exchanges I'm making. Well, at this point, I want to make a point. We know that fuel systems been around for decades, and technology evolved around them, adopting their functionality for improvement and optimization. But electrification is at the beginning of the way, and it has really good potential to grow and to be improved and optimized. And here is how. We're looking forward to use better alternatives, like sodium batteries and flax fiber, instead of carbon fiber and lithium batteries. And in case of using rare materials, we're able to reduce it up to 76%. And this is why, because we're using sodium, which is not lithium, more plentiful. In the sodium batteries, they're not going to be used any cobalt and little amount of nickel. So we are able to have a significant reduction, getting close, fairly close to the fuel propulsion system. And also, in terms of energy consumption, we're able to reduce it for 40%. And we can say that it is half of the amount. We can reach half of the amount that we're using right now. And this is a good news for the electric propulsion systems. And we are reducing the exchange and trade-offs in this way. And the important one, a good news for the marine habitat, we're able to reduce 38% of marine eutrophication. And in this case, like mineral resources, we are fairly close to the fuel motor. And surely it is a good news for the marine life. We chose to go critic on ourselves first. And while it wasn't so coming good for the electric propulsion system, but we did it. But after thinking about using alternative material, smart material, the electrification stand out. The trade-offs were narrowed, the exchanges were reduced significantly, and the electrification made a better picture for the future. So electrification, as it has a really good room to evolve, it is in a good path, and we believe we are at the beginning of something that is far more sustainable.
Thank you so much for that presentation. Would you mind skipping back a little bit to show us the graph with the global warming potential? A little bit, it's quite early on. One more. Oh no, there we go. Okay. What I'm interested to understand is about, so you've mentioned your functional unit. We're looking at 200 hours of use over 10 years, so 20 hours a year.
2,000 years.
2,000.
Thousands. So
you're talking about, okay, no, that makes a big difference.
200 a year would be.
No, so we're talking 200 hours of use a year. And do we know, I can't do maths quick enough, but the idea would be to understand what the impact is and how many years it takes to offset the production impact. I can't do the maths fast enough. But that's the statistic that would be really useful to know, so that we can really understand which vessels should be switching to electric motors and for which of them actually the impact, they use their vessels so little that the impact is not sustainable necessarily to make that switch to electric. So that's the statistic that would be really good to know. I don't know if you have it in the data or if you know it, but.
Yeah. In this analysis, we considered the Fokker 510, which is a small vessel, and we considered 2 outboard motors that being used on this specific vessel. And these results are dedicated to electric motor and the fuel motor, which is only dedicated to the Fokker 510. There is some trade-offs with using the electrification on bigger boats or smaller boats, but in this case, we have the data about this specific case of the vessel.
Yeah, no, that's great. And my other question is, you've talked about sodium batteries, flax fibers. What's the timeline looking like for when that's a feasible option?
Expecting this question. I have some colleagues are working in this topic in the University of Bologna, following up this topic, very interested. But they told me they are working. Most of these projects in the University of Bologna are classified, unfortunately. But I know they're working on it, and the future insight about when it's going to happen, I can say it is close. That's why we are talking about it here in Energy Boat Challenge right now.
Perfect, thank you. Does anyone else have any questions at the front?
Thank you. I was interested in the link between the electric propulsion and electrification. I didn't get that link.
We did this analysis for a specific reason, but as it went in, it shows really sophisticated result of being electrified or not. So we also showed this result to tell that the trade-offs between go electric or not exist. So we can extend this result and be more optimistic about the future of other things to be electrified. Like the cars, already they are, maybe airplanes, and we can work on it. And I thought it may be a good representation of a good future with the expanded industry of electrified vehicles.
Okay, this I get, but I didn't get the link. Like, what would be the issue of electric propulsion systems causing eutrophication? Like on one of the slides where you talk about the algae. Eutrophication, yeah.
Yeah. Okay, here. This is related to terms of production of lithium batteries.
Okay.
When they try to purify lithium they need, and also the other materials. This is more related to the wastewater from the manufacturer.
Okay, got it, from the mining and all that stuff. Okay,
yeah.
Got it. Okay, thanks.
Good afternoon. I got a question about the composite side. In your presentation, you talk about replacing the carbon fiber with flax. Why this choice? Why you didn't go for basalt fiber, for example, or else?
Well, because the flax fiber are natural, and we think with use of natural material in terms of marine vehicles will be a better choice for being more sustainable. And also, University of Bologna also already working on the flax fiber, so it is much more maybe attainable for us. Also the other composite, but our choice for now is the natural one, which is flax fiber.
But maybe I can give you, and to all the other teams that want to create a company, some of experience. You know that just in front of you, you have the boat Energy Observer. With on board, you have some sails that was named Ocean Wing solution, and that solution now is still on the market, but it changed dramatically. It might be 30% less efficient than it was at the beginning, but it's just been realizing to touch the market now because it costs a lot less. So maybe you're right by having some flax fibers or from fibers, but please consider that the industry will, let's say 80% sure, will request aluminium. Maybe you can recycle aluminium, but that might be for the frame a sort of good materials that you will have to think about. So when you want to create a solution, always think about, okay, I need to maybe take some percentage of efficiency out to reduce dramatically the price and to try to think about industrialization. Sure. And in that case, aluminium become very, very competitive.
For sure, we are considering all of these options, but at the beginning, we are, as in a startup, we're trying to try all the possibilities and put it in operation to see the result. Because in our case, the amount of the material, maybe not that much significant to impact our product so much. So we're willing to see the feedback when we put it in operation, and then we can decide and do all the solutions you propose now about our product.
Thank you and congratulations.
Thank you. Thank you.
We have now come to the end of this session of the 2025 Tech Talks. Before we leave, I'd like to thank all the jury members for being here, the students, and remember students, we have the E-Championship finals tonight in the meeting room. And now I believe that the only right way to end this edition of the 2025 Monaco Energy Tech Talks is by ringing the bell.